Okay, let's get started. So, this is a continuation of the PDE stream we had on Saturday, just last Saturday. So, um, over there, well, we spent like first 2 hours discussing what the field is about and a bunch of textbook recommendations, and I chatted a lot with you guys over chat. So that was fun, but it did mean that original plan was not finished. So this is, well, of course, a continuation of that. This stream, we're gonna do mostly just math. Okay, we're gonna minimize the tangents and chit chat and all of that. Just gonna be very intense math and problem solving and that sort of thing. So it appears that this is a topic with very strong interest. So I'm considering it, making it somewhat of a semi-regular. I mean, right now there's a lot of topics going on the channel, and especially when it comes to if especially considering the PD is such a large topic, right? So so this is going to be a fun one. I still would prioritize the original, how to say, the existing series, namely the measure theory and what's that, complex variables. And speaking of which, so measure theory, complex variable, stochastic process, stochastic calculus. Although PD is very much related to all of those fields, right? So this gives us some sort of motivation of pursuing these more fundamental subjects. So PD is really, in my opinion, a hub, that a nexus that connects so many different fields of mathematics. So by the way, another announcement. So today we're doing the PDE stream. So I hope to stream every night, every evening, except Sunday. So that's the plan. Because right now I cannot do what I did last week, namely multiple streams a day. That's just unfeasible, right? So I mean, unless I can do this full time. I was saying, like, so last week, because I was on vacation, I tried to make as much progress as possible. So I kind of, that was a special situation. So right now I'm here, we're back to normal again. So as I was saying, we're gonna continue, of course, the measure theory stream. The measure theory stream usually happens on every Tuesday evening. So we're going to continue doing that. So tomorrow is going to be measure theory. And we're in a position. So where's the measure theory note? Because that was the last measure theory note. We did a bunch of exercises last time regarding sigma algebra and measurable functions, right? So we're in a position to introduce measure in measure theory. This is, of course, the real beginning of measure theory as well as the measure theoretic probability. Okay, we need a lot of background and we need a lot of what do I say, motivation for explaining why do we need measure theory in the first place, right? Because this is not a trivial matter at all. So the thing is, I understand that a lot of viewers of this channel came to the channel because of they originally subscribed because of the stochastic series, right, and also mathematical statistic content. So I'm going to run this stream of measure theory as well as probability simultaneously. So what do I mean by that? Well, because we're using Axler's book for measure theory, right? We're using the Axler's book for measure theory. It is a traditional exposition to measure theory. I mean, nothing wrong with that, and it's a very solid introduction, and it's very rigorous, and it's just very awesome book. Okay, and it's completely free. I wish I had access to that book when I was in the university, in particular in grad school, but I didn't. Okay, so I wish I had that book. It's a great book. However, if you're primarily coming to measure theory for the purpose of learning rigorous probability. This is a valuable book, but perhaps you would probably still need something else to complement that. The reason for that is simple, because Axler treat probability theory as an application of measure theory, and unfortunately he put it at the very end. He put it at the very end of his book. If you go to Axler, actually, yeah, Axler's book is completely free. Of course, I said that multiple times, so let's just go to Axler's website on measure theory. So that's the book, right? Measure, Integration, Real Analysis by Sheldon Axler. If you go to the PDF version, you'll clearly see that measure theory is in the last chapter. But of course, doesn't mean you have to read everything before. Everything before that chapter. Sorry, I was trying to say, of course, it doesn't mean you can only study measure theory, the probability theory in a measure theoretic way, aka rigorous probability, after you finish all the chapters before. That's not the case. But it does present a kind of a dilemma for beginners. Okay, at which point should you switch to chapter 12, right? That's not an easy decision to make. So for that reason, I'm going to do the measure theory streams in the following manner. So it's pretty much going to be kind of similar to what we do on Saturday. So we on Saturday we tend to split our streams in half. So the first half is mathematical statistics, and the second one is exterior ballistics. Kind of weird combo if you don't know my original motivation, but that's besides the point. The thing is, I think I'm going to do a similar format for measure theory. So the first half is going to be on Axler, just the traditional approach to measure theory, and the second half would be the more dedicated introduction to probability theory, because there's a lot of overlap right now between the traditional measure theory as well as measure theoretic probability. Okay, if we just start from measure theoretic probability right from the start, there's going to be a lot of intuition missing, motivation missing, and that kind of thing. I think starting from the traditional measure theory, aka the route taken by Axler, is still the best way to build intuition. And now that you already know, okay, why do measure theories needed, then we can kind of study those two in parallel. And it's a good exercise to translate notations as well, because in advanced mathematics, quite often, I'm not saying this is the norm, but quite often you will see different authors using different notations, and it's a very basic skill for beginners and veterans alike to be able to translate between them. So what results are essentially the same, are basically the same, and what results are unique in a given text or exposition. So that I think that's a good exercise. So that's the plan for what's coming next. And in fact, if you go to the stream thumbnail for tomorrow's measure theory stream, you'll see the thumbnail is split in half. So the first half is the Axler's measure theory cover, and the second is a separate book. It's a separate book called Real Analysis and Probability, written by Professor Robert Ashe, which I also recommended in my video a while ago, called Measure Theory Made Doable. So over there I did a book review as well as a kind of a study plan, so to say, for measure theory and measure theoretic probability. And on this channel, when we recommend something, we actually will actually spend time going over it, because I'll be honest, this is personal bias, because I'm kind of right now sick and tired of all the book reviews content on YouTube. I don't mean you cannot enjoy them. It's just me having enough of them, because I feel like you cannot say anything substantial in the course of just a few minutes or like tens of minutes. It's just impossible to say anything substantial over there. What are you going to do? You're going to read the content list and say a few words about each topic? Like, how is that even helpful? And what makes the book stand out? Like, you cannot talk about these things just by the nature of the subject matter in a short period of time. So this is I would say. I'm just gonna say it out loud. I'm not gonna make a book review video anymore. Okay, I used to enjoy them and I made a few of them back then, but now starting well, recently, I will not make a book review video anymore. But instead, we'll do these kind of marathon style walkthrough, or even just a few sections. I think that's more valuable than a book review. Okay, because I cannot say anything. I mean, if you can, then it's good for you. But I find myself unable to say why Axler is a great option for beginners, except for super generic advices. That's for me does not very helpful. Hi, Ceiling. Thank you very much for joining the stream. All right. So enough of that. Okay. Enough of announcement, chit chat, and personal philosophy. Let's get back to the math. Okay. So where were we last time when it comes to PDE? Okay, where were we? Because I understand that Saturday near the end we were a little bit rushed. So let's just recap of what we introduced over there. So on Saturday, after deriving the PDE for the traffic flow, which is essentially a conservation law, of course, we will come back to this sort of derivations in the future as well. So after deriving it, and it turns out that this is a first order PDE. This is a first order PDE because it only involves first order partial derivatives. And actually, it only depends on the first order partial derivatives in a linear manner. So the partial derivatives themselves only have linear terms in the PDE. So there's no such thing like a partial derivative being substituted into a nonlinear function. There's no such terms. So for that, we define what a linear first order PDE is. The traffic flow PDE is almost linear, but it's not quite. It's called quasi-linear because even though the partial derivatives themselves appear as linear terms, the coefficients depends on the unknown function itself. So that's the difference between linear and quasi-linear PDEs, and that little difference will actually make a huge difference when it comes to solution behavior. So our objective today is to study linear first order PDE, and in particular through the example of this model right here, model 2, called continuous time birth and death process, which is a stochastic process, very commonly used in a lot of areas such as population dynamics, as the name suggests probably, as well as epidemiology. Epidemiology is the study of infectious disease, such as COVID-19. The study of how do disease spreads and etc. Right, from a mathematical angle. Mathematical epidemiology is a dedicated field. It's a highly specialized field in the field of applied mathematics, part of mathematical biology. And also, birth and death process is used in modeling chemical reactions. And so this is a very powerful tool. So we did a brief introduction of what a continuous time birth and process is. Well, continuous time birth and death process is a special case of continuous time Markov chain. Without diving into the general theory of continuous time Markov chain, we introduced the birth and death process as follows. So x of t is a stochastic process. You can think of x of t as the number of individuals in a population. And x of t takes values in a set of non-negative integers, 0, 1, 2, and so on. So this is the typical trajectory of a birth and death process. So it starts from a given value, say n naught. Typically n naught is given. The initial size of the population is given. It's a non-negative integer. Usually it's non-zero, okay? Because usually you don't start with 0, but it can be. It can be 0, but typically n naught is non-zero. So what happens is at each instance, only 3 possibilities can happen when it comes to the transition of x of t. First, you have the non-transition. So at a small time interval, the overwhelming possibility is that nothing happens. So if you look at this sample path, right, transition happens at these instances. And of course, these instances has a size of 0 compared to the overall time interval. Right? Using the language of measure theory, we say that the size of discontinuity is 0. Right? The measure of the outer measure of the discontinuity is 0. So the overwhelming majority, the overwhelming probability is, how do I put this? So in a small time interval, the overwhelming possibility is nothing happens at all. So that's the first assumption. And if a transition happens, x of t can only go up or down by 1. That is to say, x of t either experience a burst, that is going from n to n plus 1, where n is the current population size, or it goes from n to n minus 1. That's the other possibility. Okay, no other possibility is possible, or at least have overwhelmingly small probability that we can ignore them. Okay, so that's the intuition here, and we typically represent a Markov chain using what we call a transition diagram or a state diagram. So these are the states 0, 1, 2, 3. They're just the possible values of the size of the population. And from 0 we can go to 1, but not to 2. Okay? Because population size cannot be negative, so it can't be minus 1. Right? And so from 0 you can only go to 1, and then 2, and then 3, and so on. Right? And for any other non-zero states, it can either go up or down by 1 unit, as explained. So to describe the dynamics of births and deaths, we have these two functions, lambda n and mu n, or sequences to be exact, lambda n and mu n. They're called the rate of birth or the rate of death, and they're interpreted as follows. Suppose the current state, x of t is n. Then for a small time interval with duration delta t, delta t is very small, the probability of going from n to n plus 1 in the time interval t to t plus delta t equals lambda n times delta t plus higher order terms of delta t. So that's the fundamental assumption. Okay, so this is the interpretation of the quantity or the function, the sequence lambda n. So that's the birth rate. Okay, so usually in a problem, usually in a model, lambda n is given. So design what lambda n and of course mu n is part of the modeling process. Okay, they carry usually some sort of physical assumption in there, and we'll see one example for that. Okay. Let me just answer the question. Kraken asks, hi, first of all, thanks for joining the stream. It says, would you recommend taking a course in Bayesian statistics or stochastic process? Of course, absolutely. Absolutely. And it really depends on your specialization, actually. So depending on your specialization, in some area, actually, Bayesian statistics is the dominant model. Okay, so I have a friend of mine who told me that in the field of, for example, in weather prediction, so he is in the physics community, physics faculty, and over there, the statistical methods used highly values Bayesian statistics. So it really depends on what sort of area you're working on. But overall, nowadays, Bayesianism, or Bayesian statistics overall is a valuable skill. Okay, it is still not universally adopted, but it is not fringe anymore. So definitely go worth it. All right, hopefully I'm back. Yeah, sorry, I still haven't, Kraken, You're welcome. I still haven't finished answering the question, but yeah, the stream was frozen due to poor internet connection. So I was about to say that in our stream on mathematical statistics, we're using this text by Professor Evans and Professor Rosenthal from the University of Toronto. So my intent is to cover chapter 5, 6, 7, 8. We already did 5. We're in 6. So 7, well, the next chapter is the Bayesian inference. So we will give an exposition for that, just the main ideas and whatnot. Okay, so yeah, Bayesian statistics definitely worth it. I'm planning to cover it, cover the fundamentals of it. Okay, of course, this is a huge field. As well as stochastic process. Yes, stochastic process is, of course, a huge part of probability theory. And if you're serious about probability, data science, machine learning, you should definitely check out stochastic processes. Yeah. And of course, none of these courses are easy. None of these subjects are easy. Okay. If these are electives and your priority is, well, say your GPA, then, well, feel free to not take them. Okay, I'm a practical person too. So if your objective is to prioritize your GPA, to make it look clean and whatnot, then perhaps, I don't know, like these are, especially stochastic process, usually considered the killer. Is the killer of your GPA is more likely to, say, take a dip if you take this one compared to others. I mean, of course, that's a very oversimplification, right? So just be prepared that none of these are easy. But we're not here on the channel to do easy things, aren't we? Okay. So yeah, coming back to the topic, birth and death process. So I just finished explaining the meaning of the rate of birth, lambda n, and the rate of death is interpreted in a similar manner. So the rate of death, mu n, has a similar interpretation, namely in the time interval t to t plus delta t, the stochastic process x has a probability of experiencing a death that is going from n to n minus 1 of probability mu n times delta t plus the higher order term o delta t, little o delta t. Okay, this is little o. Maybe I should explain this a little bit. What does this mean? So this just means that this notation, little o, little o notation means the limit if, let's say, if a function of delta t, say, f of delta t equals little o of delta t, it means it goes to 0 faster than delta t. So intuitively, you may think of this as the higher order terms of delta t, say delta t squared, because delta t squared over delta t, as delta t tends to 0, is 0. Okay, so O of delta t is really just a class of functions, not a function. Okay, so these are we usually colloquially in applied mathematics call it the garbage collection terms. So the higher order terms are the ones we consider quote unquote don't matter. Okay, so this is what a rigorous definition is. So if f of delta t is written as little o of delta t, we mean that it tends to 0 at a faster rate than delta t. Okay, and as I was saying, the overwhelming probability in the time interval, the overwhelming likelihood or tendency, so to say, of the process in the same time interval is to stay constant. So the probability of staying constant in the same time interval is 1 minus the probability of going up minus the probability of going down and plus higher order terms of delta t. Any other transition would have a probability of just little o of delta t, higher order terms of delta t. All right, so that's the problem setup, okay, the model setup. And a major result in the theory of Markov processes is the Kolmogorov forward equation, sometimes also known as Chapman-Kolmogorov equation. Actually, they're not quite the same thing. Chapman-Kolmogorov equation is more fundamental, whereas Kolmogorov forward equation is the differential version, right? The differential equation version of the CK Chapman-Kolmogorov equation in continuous time. So if the process is in continuous time, then it is possible to derive a system of differential equations or partial differential equations based on the what we call the Chapman-Kolmogorov equation. So that's a fundamental result, and I'm skipping that derivation here because it would take us quite a bit to derive that. Okay, so basically, Kolmogorov's forward equation is what? Is a system of ODEs. It is a system of ODEs that describes the time evolution of the probability mass function of the random variable x of t. So think this way. Usually, as we're saying, the initial size of the population is fixed. Usually that's fixed. So as you can imagine, this means at time t equals 0, we have infinite precision. We 100%, right, with probability 100% knows the distribution of x of 0 is centered at n0. There's no uncertainty here. Right? But as time goes on, right, you got more possibility. For example, let's say this is one trajectory. This blue curve is one trajectory. So you got the next possibility is something like this. So it goes up here, and it immediately drops down. Okay, and it keeps stay constant like this, and it drops down like this, and then it keeps being constant like this, and it keeps dropping down, and it dies. Okay, like this. Is it also a possibility? And my point is, as time evolves, the random variable x of t becomes less certain. Right? So this is just common sense. So how do the probability mass function, the probability mass function of x of t changes over time? And that's the Kolmogorov equation that describes the answer to that question. Now, the Kolmogorov forward equation describes how the probability mass function of the random variable x of t evolve over time. Okay, so it does not describe the process value itself, because the process value is discrete. The Kolmogorov forward equation describes the evolution of the probability, or probability function that governs the distribution of x of t. So this is a coupled system of differential equations, and in fact, due to the state space is infinite, so you have infinitely many possibilities, 0, 1, 2, and so on. The Kolmogorov forward equations, actually it should be plural. Okay, Kolmogorov forward equations is an infinite system. You got infinitely many ODEs coupled together in the system. Of course, this is very difficult to solve in general. Okay, so what can we make progress from now? What can we make progress from now? Actually, there are dedicated techniques in physics, physics literature on how to solve this kind of equation. The Kolmogorov forward equation in physics often is also called Master's equation. Dedicated techniques for solving these equations, sometimes approximately. Very interesting stuff. But here we're going to look at a special case, that is the Malthus process, aka linear Bresson-Des process. What do we mean by that? Well, it means that the lambda n is just n times lambda. The population size, the current population size, times a constant lambda. Lambda is a positive number. By the way, here mu n and lambda are both positive sequences. And mu n is also linear. Is also linear in n, where mu is a constant. So, as we shall see, this is the famous This is the stochastic analog of the famous linear population model. The differential equation for the population model, the exponential growth, actually. So Malthus was actually famous for proposing this exponential growth model for population, and he was a British economist. He had this very famously pessimistic theory about the future of human beings. His theory predicted that from his differential equation that population grows at an exponential rate, right? Whereas food production only grows at a linear rate. According to his economic theory, then that's what's going to happen. And as a result, human population always grows faster than the level of production. So as a result, cyclically in history, we will see mass famine and wars for fighting over resources, and it's going to be mass starvation and start over again. So that was his theory, which was, of course, very pessimistic and actually not very realistic either. Because actually, major famines in human history was not due to a lack of food per se, but rather due to the political situation. Usually, there was this famous description, I think by one of the Nobel economists, saying that there was no famine ever happened in a democracy. So it's quite interesting that Malthus' model is actually completely false. Famine in human history was never due to the lack of food, but rather due to horrendous political situation. Anyway, that's a digression, but this is the model. This is the fundamental assumption. And in the Malthus, aka linear birth and death process, that is, the birth rate is proportional to the population size, and the death rate is also proportional to the population size, where mu and lambda are constant. And this has a physical meaning. Unfortunately, the explanation of this would require a in-depth analysis of continuous time Markov chain. But basically, this is what it means physically. This means each individual gives birth at a rate lambda. These are independent events. At any instance, each individual has a possibility of giving birth, and that happens at a rate of lambda. In the same sense we described earlier, so that is to say, in a small time interval going from t to delta t, one individual has a probability of lambda times this very lambda, okay, the constant lambda times delta t of giving birth. And also in the same time interval, it has a probability of mu times delta t to die. So that's the interpretation of lambda and mu, the rate of birth and death for one individual. And each individual's the individuals die and give birth independently. So this is a very famous assumption, and actually most of the population dynamics model are extension of this thing. All right. So this means you can substitute lambda n and mu n into the Kolmogorov forward and backward equation. So the forward equation, no, not backward equation. We haven't even talked about backward equation, and that's actually something we're not gonna discuss in this model. So basically, you just substitute the expression for lambda n and mu n into the ODEs. Okay, but still, this is a difficult problem to solve. Like, how can we obtain a formula for Pn of t, right? And also, this is an infinite system, so it's not easily handled on the numerical algorithm either. Typically, you can't, unless for very specialized situation, you can't just substitute it. You can substitute it in your favorite ODE solver, say your MATLAB's RK45, ODE45, and get a solution. It's not easy. So here we're actually going to introduce an ingenious tool, generating function. I believe generating function was invented by Euler. The notion of generating function is an extremely profound technique. Okay, is in mathematics in general. In fact, things like Fourier transform and Laplace transform are all special cases of generating functions, but that's beside the point. Now, hi Vernon. So to describe Pn, which is a sequence, we can use a power series to do that, because there's always a one-to-one correspondence between a sequence and a so-called formal power series as follows. So if you have a sequence with index labeled by non-negative integers, that's p0, p1, p2, and so on, this is just a sequence of numbers, sequence of real numbers, you can encode the same information using the formal power series. The formal power series is the sum of Pn s to the n, where s is an auxiliary variable that does not tend to not have physical meaning. But the point is, if you know the power series, you can extract the coefficients of the power terms, and you return back to the same sequence. So these two objects, even though one is discrete, one is continuous, power series is considered as a function in S, by the way. So let me put that down here. Now this is considered as a function in S. So this is a continuous object. S maps to this thing, okay? And we stress that this is a formal power series, namely we do not care about the convergence of this series. Right? We only care about its coefficients. There's a one-to-one correspondence between these two objects, a sequence and a power series. And guess what? For a given time t, for a given time t, where is that? Yeah, right here. For a given time t, Pn of t is a sequence. Pn of t is a sequence with an index n equals 0, 1, 2, and so on. So for a given t, you have a sequence. And as a result, we can encode the probability mass function by something called the probability generating function. So, and that's the definition. So this works for a general non-negative integer valued random variable. Okay, for a non-negative integer valued random variable, big X, its PMF, probability mass function, is defined as P subscript n equals the probability of X equals n. And based on the duality, one-to-one correspondence between the sequence and the power series, we define the so-called probability generating function, PGF, in the way we just described. So G of S is Pn times S to the n. Pn times to S to the n, which is equivalently the expected value of the random variable S to the x. So this is the function of the random variable, okay, S to the x, a power function. So that's the probability generating function. It only works for non-negative integer valued random variables. Okay. So that's the PGF of a random variable x. So now for the burst and test process, well, x of t is, for any t, it is non-negative integer valued. So apply the definition of PGF, you get a function that has two arguments, s and t, where s is the auxiliary variable in the PGF in general, and t is the time. So last time we merely stated that G satisfies a PDE, in fact first order linear. We didn't have time to derive it, so now we're going to pick up from there and do some analysis of this PDE and introduce how do you solve first order linear PDE in general. Okay, so that's a very long introduction to what we did last time. So as I was trying to make the presentation self-contained, because I mean we have still 3 hours and a half to go, so there's no need to rush there. All right, so starting with the forward equation, yeah, as I was saying, that's the forward Kolmogorov equation, and you just substitute lambda n and mu n into there, and you get this system. Okay, sorry, I forgot to put the dot here. And then I'm trying to connect this to the PGF. The goal is to derive a PDE for PGF. Oh, hi Leo, thank you very much for joining the stream. I'm doing great. Let's multiply s to the n on both sides and see what will lead us to. All right. So so first of all, let's just say here actually here let's say this is, I want to multiply Pn dot by s to the n. This is the time derivative of g. This is the time derivative of g. So you're taking time derivative with respect to the series. S is left alone. So this is just dg over dt, partial derivative. Okay, and here Pn dot has two cases. So let's break the sum into two portions. So you got the n equals 0 term, which is just P0 dot times s to the 0, which is just 1. And then plus the sum, where n goes from 1 to infinity, Pn dot s to the n. Right? So now we can substitute the two forward equations. So use the forward equation, say Fe. The first term would be mu times P1. Bear in mind, mu is a constant, P1 is a function in t. Okay. So yeah, there you go. And the second term, of course, would be a bit longer. That's the sum of n from 1 to infinity. This is Pn dot, so that's lambda times m minus 1 times Pm minus 1. All right, and plus mu times m plus 1 Pn plus 1 minus lambda plus mu times n times Pn. Okay, and then times s to the n. So that's the substitution of the forward equation. And now we're trying to connect this to big G. Okay, so let's see how that's done. All right, so remember what's big G. Big G is this thing, right? It's the sum of, this is the sum, okay, let me just put it on the side. Okay, so big G is the sum of Pn s to the n, where n goes from 0 to infinity. This is big G. Okay, big G depends on both t and s. When t appears in Pn, which I did not write, okay, that's just a shorthand. Okay, so that's G. So how do we connect the right hand side to G? Right? That's the big question. So why don't we break the sum into 3 terms, because that should be more transparent. You're my big G main. Well, thanks, Leo. By the way, congrats for to the growth of your channel. It's awesome, well deserved. Guys, if you still don't know about Leo's channel, go check him out. So Leo holds podcasts with other creators, research mathematicians, as well as and he also teaches stuff. He also teaches the various pure mathematics, in particular abstract algebra, theoretical computer science. I mean, I think theoretical computer science should be considered, well, sociologically in the category of pure math, right? So it's a different flavor of what we're doing on the channel most of the time, although I'm pretty sure down the road we'll have some overlaps. Okay. So, and I'm trying to pick up more algebra as well. So yeah, and always Leo is very helpful when it comes to providing a more technical input. I remember doing a mathematical statistics stream on the topic of sufficient statistics, and I was totally unaware of the more like the information theoretic point of view of sufficient statistic, and he was just trying to teach me in chat and I couldn't follow. Okay, so we'll have to do a wrap up on that. Okay, we'll do a wrap up on the topic of sufficient statistics from the point of view of information theory. So hopefully we'll do Leo some justice. Okay, yeah, teaching Ming algebra stream someday. Yeah, actually, you know what? Teach me group theory. Very much looking forward to it. Okay, how about that? All right, let's come back to this derivation here. So we're trying to group the right-hand side and try to express the right-hand side in terms of g or the derivatives of g. So that's our goal here. So that's just an exercise in first year calculus. Right, so this is the exercise in first year calculus. Let's see how that's actually done. Here, the first term. So on the right-hand side, you got a bunch of terms. So this is what happens on the right-hand side. So look at the first series. Okay, ignore the standalone term for now. Let's just take a look at the summation. It goes from n to infinity. Lambda times m minus 1 pm minus 1 s to the n. Okay, so that's the first term in the summation. Let's see how can we manipulate that. So we're going to first change the index, say from, let's substitute, let's say change the index so that m minus 1 becomes n. That's the idea. And also taking out the constant lambda. We're going to take out the constant lambda and say the new index is m minus 1. Okay, so here n is m minus 1. Actually, you know what? We're trying to make this super easy to follow, so let's write m equals m minus 1. The new index is m. So this way, each term in the summation now reads m times pm s to the n, well, n is m plus 1. Okay, and the new index goes from 0 to infinity. Okay, m is just a dummy index. It doesn't matter what the what the letter you use, of course. So here, yeah. So here, as we can see, it seems to suggest that we can get this new sum by a term-by-term differentiation argument. Okay, so here, actually, can I do that? Can I do that? I think this should be a term-by-term differentiation. Let me just write the formula on the side. Okay, so let's say you have a function f of x, which is the sum of an x to the n, and n goes from 0 to infinity. Assume term-by-term differentiation is valid, so f prime of x would be the sum of n goes from 1, actually 1 to infinity, an times n x to the n, because the first term is a constant, n equals 0 in the original series a constant. After differentiation, it just cancels. Okay, so you just do minus 1 here. Perhaps we could connect the two. Perhaps we could connect the two. That's my motivation. So perhaps we can say, compare the two results here. So perhaps I can, you get a s to the, here I have a s to the, s to what? Well, let's just do it that way. So when m equals 0, the term is 0 anyway, so you can write it as m from 1 to infinity, and m times pm, s to the m plus 1, all right? And then take out the factor s squared. So taking out the factor s squared, it becomes lambda times s squared, the sum of m times pm, sm minus 1, where m goes from 1 to infinity. And what is this? This is exactly the derivative of big G. So that's partial derivative d big G over ds. There you go. So this is what I'm trying to do. I wish to do the same manipulation for all the terms that comes after. Okay. All right, so that's the first summation. What now? Well, now, here, let's take a look at the second sum. The second sum looks like this. That's the sum of n from 1 to infinity, mu times m plus 1, right? And you got pm plus 1. Oh, hi, Christian. Thank you very much for joining the stream. And Leo says, Ling, this reminds me of, I suppose you mean Ming, this reminds me of my blog post about mixed Poisson distribution. Oh, sure, I'll go check it out. Yes, it also recovers expectation via derivative, actually, yes. Yes, so, yeah, we're going to finish deriving this, and we'll see how this leads to the derivative of moments as well. So actually, there's a lot of information encoded in this PDE. You can derive the ODE satisfied by the moments. But let's just finish this. Yeah, I know. Yeah, mod me. Okay, sure. How am I supposed to do this? How can I make you a mod? Yeah, add as moderator. Managing moderator or standard moderator. Okay, I'll just put standard managing moderator, okay? Yeah, Christian will do that for you as well. Yeah, you see, Leo, you're now a moderator. And Christian, I'll make you mod too. Okay, so Christian is also now a mod. All right, there you go. Okay, thank you guys for volunteering. Actually, Leo, you know what? Let's just go check out your blog post right now. Hang on a second. Yeah, go to site. The mixed Poisson distribution. That's cool. A short axiomatization uniquely characterizes Poisson distribution. So using the generating function as well. So Leo is using a generating function as well. Yeah, this is very much in the same strand of what we're doing here. Yeah, I think this is well known. The Poisson process characterization has several equivalent, let's say, equivalent characterization. You can describe Poisson process as a pure burst, burst and dense process with just constant burst rate. So lambda n would be a constant. So if you want a Poisson process, you just need a pure burst process with lambda n equals a constant and no death. Okay, so the only two possibility in a short time interval is either going up by 1 or 0. Okay, so as you can see, this is very similar to a binomial trial. Either go up or 0. Just two events. And what essentially happens is the binomial approximation of Poisson distribution. So you might have heard of that. So the binomial approximation of the Poisson distribution says, in a binomial distribution, if the number of trials is large and the success probability is small, yet at the same time, the product is non-trivial. Okay, so the product, the number of trials times the probability of success is non-trivial, is non-negligible, then the binomial distribution is approximately Poisson. So that's the first characterization. And there are also other characterization. For example, you can characterize the transition time. So if the transition time are all IID exponential with rate parameter lambda, then you would also give a Poisson process. Once again, assuming only birth is possible, okay, no death. That's also a characterization of Poisson. And last but not least, which in my opinion is super interesting, is that if you select a finite time interval on your x-axis, the time axis, so let's say this is the time interval that you're looking at, because in the Poisson situation, that is pure burst, in the situation of pure burst, you only need to identify the transition time, the jump time. Then the whole process is completely determined, because when the transition, it only goes up by 1. So it's just a matter of characterizing the transition time. As I was saying earlier, the inter-arrival times are ID exponential. So that's one way to characterize it. However, let's say if you have a finite time interval and you want to generate or simulate a Poisson sample path within that time interval, there's a faster way to do it. What do? Well, you just select uniformly random points. And that's just uniformly random points in the time interval, uniform distribution. So think of this is A, this is B, okay, and you generate uniform random variables in that interval. And those instances will be treated as transition time. And probabilistically, this is the same as the Poisson point process. Okay, so I just gave 3 characterization. Okay, I just gave 3 equivalent characterizations. It's actually a good topic for a video, proving they're all equivalent. But here, Leo's blog post pretty much follows our. I mean, he didn't follow, but we are doing the same approach. Okay, that is to define the generating function. And here I'm trying to derive the PDE for the generating function as follows. Okay, so so here in the second term is the sum of mu times m plus 1 times p m plus 1 s to the n. So here we're going to do the term-by-term differentiation again. So here let's consider putting m plus 1 as m. Okay, so m can be m plus 1. Here you have the new notation for the same series. So m goes from 2 to infinity, because when n equals 1, m plus 1 is 2. So mu times m, pm s to the m minus 1. Right, because n is m minus 1. So how did this compare to the differentiation formula? Well, mostly the same, except the lower index is now m plus 2 rather than n equals 2 rather than 1. So how do we'll have to change this to m goes from 1 to infinity. All right, I'll take out the mu up here, taking out the constant mu, and then little m times pm s to the m minus 1. Okay, and because now I added an extra term, I need to remove that. When m equals 1, that will be p1 s to the 0. Right here. Yeah, thanks Leo for stopping by. Great discussion, and thanks for letting me know about the blog post. It's awesome. Poisson process is actually the starting point of what we call the point process. A subscriber requested a topic called the Hawkes process, which is really a generalization for that. We'll see if we'll hope to make a stream on that in a future time. But this is a great way to get an idea of what point process is all about. Okay, so here I'm doing this manipulation once again. The first term is the partial derivative, dg over ds. Okay, and the last term is minus mu p1. And that's quite nice actually, because mu p1 is an additional term at the front, so it actually cancels out with this term, mu p1. So that's nice. Okay, so that's the second sum, and we'll do the third sum in a similar manner. So that's the sum of m equals 1 to infinity, lambda times mu n times pn s to the n. Of course, be careful about the minus sign here. So you got lambda plus mu. Let's do the same business of, actually, we don't need to change index anymore. We just need to take out an extra factor of s. This way, it now reads the sum of n from 1 to infinity, pn, n times pn, n times pn times s to the n minus 1, and that's exactly the partial derivative. So this is lambda plus mu times s times partial derivative dg over ds. Okay, so that's great. Now, no summation is needed on the right hand side anymore. So let's bring everything together. Okay, so this is star. So now star just reads, okay, dg over dt equals mu p1 plus the first term, which is lambda s squared times dg over ds. Okay, yeah. And then minus, actually plus the second term. Yeah, this is the second term. The second term is mu dg ds minus mu p1. So mu p1 goes away. That cancels out. Cool. And the last term would be this one, plus lambda plus mu s dg ds. dg ds. All right, so just simplify this further. So you got coefficient lambda s squared plus mu, hang on a second. Is there any s term needs to be taken out? Actually, no. Actually, no, it's just plus mu. Okay, cool. And plus mu plus, what's that? Lambda plus mu together times g. So together times s and then dg ds. Is this the same as I wrote earlier? We're supposed to get this result. Oh, actually, this is the minus sign, my bad. This is the minus sign. I reminded myself to pay attention that this is a minus sign, okay? But I didn't do it here, so I foresaw my mistake. So this is the minus sign, and this is a minus sign as well. So, is this the same as the intended goal? This one's on my notes, so hopefully they're the same. I took this note like over a decade ago. It's good to revisit them. But anyway, so are they the same? Yeah, they are the same. Because s equals 1 is a root. So this is correct. All right, so this is correct. This is indeed what we wanted. There's lambda s, s minus 1. If you expand this, you indeed get this. Okay, lambda s minus 1 times lambda s minus mu of dg ds. And this finishes the derivation. Okay, so the point is, the PGF of the burst index process satisfies a PDE. And now it's just purely a PDE problem. Okay, and of course, as mentioned, the PGF on its own is a complete description of the distribution of x of t. So that's the whole point. There's no loss of information. When you convert the probability mass function to probability, probability generating function, PGF. So it's a one-to-one correspondence, okay? PMF corresponds to PGF. You can describe a distribution in one of the two ways, and there will be no loss of information whatsoever. Okay, so actually, you know what? Before solving this PDE, let's see, for example, how do you get the time evolution of the mean of the process? How do you get that? Well, this is a, let me just kind of box it. This is a definition. Probability interlude is a definition, probability interlude, slash. Okay, we derive this result. How can we get, say, the time evolution of the mean of x of t? Well, we'll have to do another probability interlude. So first of all, you can get this interesting quantity, that is Pn of 0. Not Pn of 0, but rather P0 of t. Remember, what is P0 of t? P0 of t, this is the same as the probability of x of t equals 0. And this has a special meaning in our problem, in our model. X of t equals 0 means the process, well, died completely. If you interpret x of t as the population of a as the population size, then x of t equals 0, which means the extinction. So that's the extinction probability. This is the extinction probability, something that would be of great interest. Extinction probability. Right. And how do you get the extinction probability from the PGF? Well, simple. You just got to kill all the s terms. You just substitute s equals 0. Here, if you just substitute s equals 0, then the power series will only have one term remaining, namely the constant term. So that's just g of s and 0 equals g of s and 0. So how convenient is that? Okay. Once you solve for the PGF, you just substitute t equals 0 and you get the extinction probability. Well, this is a quantity of great interest. All right. So there's that. And also, if we come back to the definition of PGF in general, okay, so remember, for a non-negative random variable, here, non-negative integer value random variable, this is g of s, we can actually get what we call the factorial moments. The factorial moments of the random variable x. So that's also quite awesome. So probability interlude once again. Factorial moments, I think that's something also kind of neglected in introduction to probability theory. Usually we put a lot of emphasis on moments, right? X to the n, the expectation of x to the n. But in some situations, especially for non-negative integer value random variables, factorial moments are actually easier to calculate. This is what I mean. Interlude. So let x be non-negative integer value random variable. Okay. The what we call the case factorial moment is defined as follows. Actually, I don't know what would be a good notation for it, but anyway, that's what it means. Okay, I mean, should we give it an MK? MK usually stands for moment. How should I? What sort of? Let's use MK. Okay, let's just use MK. It doesn't matter. MK is the expected value of x times x minus 1. All right, and then times all the way to x minus k plus 1. In combinatorics, the expression inside the expectation is called a falling factorial because the factors goes down from x. Okay, so this is called a falling factorial. And is usually denoted as x with a subscript k at the bottom. Okay, this is called a falling factorial. Of course, there's also the rising factorial in which you multiply x times x plus 1 times x plus 1 minus k, okay? X plus k minus 1. That's the rising factorial as opposed to falling factorial. So this is the definition of the falling factorial. Okay. So what's the advantage of defining the falling factorial? Well, think about what happens when we differentiate the PGF. Right? This is the PGF. Let's say if we differentiate the power series, what happens? Well, I'm just going to do this super heuristically. Okay, so let's say this is the PGF, right? Starting from this definition of the PGF. This is the definition of the PGF, okay? And let's assume you can interchange summation and differentiation. So this is a single variable function in G. So let's try what's G prime of S. G prime of S, well, that's d over ds, expected value of s to the x. Assume you can interchange differentiation and the expectation. Okay. Physicists would do that in a heartbeat. A probabilist would struggle 2 hours trying to justify this. So today we'll be physicists. Okay. So differentiate that, you get d over ds, s to the x. Okay. And of course, this is just expected value of big X. Use the power rule. Okay. So treat x as fixed inside the bracket. So it will be big X times s to the x minus 1. And then you set s equals 1, you get e of x. So g prime of 1 is e of x, which is exactly the first factorial moment, m1. So this is m1. All right, so let's differentiate a second time, see what happens. All right, so that will be d over ds of d squared over, okay, and then expected value of s to the x. Okay, interchange the order of differentiation and expectation with no justification. Okay, this is purely heuristic. And you got expected value of x times x minus 1, s to the x minus 2. And now setting s equals 1, you get g double prime of 1 is the second factorial moment. You see a pattern going on here? So in general, the case order derivative of the PGF evaluate at 1. This is the case order derivative, all right, of the PGF evaluated 1 is the expected value of x, the case we call the falling factorial xk. Okay, so that would be mk. This is m2. Okay, so that's a probability interlude. Okay, so that's the formula we're going to use. The point is, if you know the PGF, you can derive any moment you want. And of course, you can recover the usual moment from the factorial moment. For example, if you already know m2, then you can recover the expected value of x squared, the usual moment. The usual moment. Well, m2 plus m1 is just expected value of x. So there's no loss of information here. It's just much easier to handle compared to ordinary moment. So it's like selecting different bases for the linear or vector space of polynomial. Well, the most obvious way is to use 1, x squared, x cubed, and so on. But here you can use the following factorials as a basis for the space of polynomial, and sometimes that's actually a much better choice. So from m1 and m2, you can easily recover the expected value of x squared as m1 plus m2. So there's no loss of information. Anyway, so that's the probability interlude, and we're going to derive the time evolution of the moment of x of t. Right? So let's say if you don't want to know the full distribution of the burst and death process, right? Instead, you just want to know how the moment behaves. You can actually recover that from the PDE. Let's see how that's done, actually. So this is super interesting, in my opinion, right? I mean, differential equations and stochastic process are linked in a very intricate way, and here we see an excellent example. So how do we define, how do we say, our goal is to find the time evolution of moments. Okay, so how do we get around doing that? Well, first of all, you have the PDE, right? So PDE, which is GS, I'm going to use this as a shorthand, okay? GS simply means, GS is simply dg over ds. This is standard notation in multivariable calculus anyway, and sometimes it saves some writing. Okay, I'll use these two notations interchangeably. So GS, as we derived earlier, is lambda minus 1. Really? Sorry, it's actually S minus 1, my bad. S minus 1 times lambda S minus mu times G of S. Actually, left-hand side should be G of T, my bad. G of T. This is our PDE. So, say, we want expected value of x of t as a function of t. As a function of t, say this is, define this as a phi of t. Is that a good way to write it? Perhaps not, right? Let's use m of t or mu of t. Yeah, mu of t. This is, we want to derive the differential equation for mu of t. Okay, and also we want to know how the variance evolves. So the variance, let's denote the variance of x of t as the sigma squared of t. I think that's the most natural notation. So we want to see how the mean and variance evolve over time. Okay, so let's see. Yeah, Christian, this is indeed super interesting. And following factorial, as I mentioned, is especially good for handling non-negative integer value random variable. For example, Poisson distribution, binomial distribution, hypergeometric distribution. And I also believe, if I recall correctly, I did this. Yeah, it's frozen. I'm sorry about that. Now I'm back. So I was saying, like, the following factorial actually plays a very important role in the mathematical analysis of the German tank problem, which is very interesting. Okay, so I mean, I hate to do more digression, but I hope one day I'll be able to cover the German tank problem as well. So yeah, as a general tip, when it comes to non-negative integer value random variables, the case factorial moment, in my opinion, is an underrated tool. Okay, so usually it's easier to obtain the factorial moment compared to regular moments. It's really just a matter of changing the basis for the vector space of polynomials. All right, so what's our result? Well, here earlier we said for a time-independent random variable x, right, if you differentiate its PGF and evaluate it at 1, you just get the first moment. And this is what we want, right? We want expected value of x of t, the mu of t. So mu of t equals x of t by our previous results. Should be the derivative of g with respect to s here, with respect to s evaluated at s equals 1. So that's, translate this result here. You pretend you don't know t. You get dg over ds. G is a function. Yeah, g is a function of s and t. See, g here is a function of s and t. So here, when you set s to be 1 and t to be, well, you don't know t, just leave t here. Right. So this is what we want. We're going to differentiate g with respect to s, partial derivative, and then set s equals 1. And that gives us the first order moment, or equivalently, the first falling factorial. The first falling factorial moment, okay? Or just first factorial moment. So the second one, the second falling factorial moment would be x of t times x of t minus 1. Okay, and that's going to be the second order partial derivative, d squared g over ds squared. ds squared, okay? And this is also evaluated at 1 and t. 1 and t. So, well, we're going to use this to get to the differential equation for the variance. Okay. Time evolution of moment. So we're going to use these to get to the differential equation for mu and sigma. They should satisfy ODE because after all they're only single variable functions in time, of time. All right, so how do we get that? But why don't we differentiate the PDE on both sides with respect to s, because you care about d over ds, right? So let's do that. Okay. So d over ds to the PDE. The left-hand side is now GST, which means differentiating with respect to t first and then s second. Actually, it should be, it doesn't matter. I mean, we're assuming smoothness actually. So, but the appropriate notation should be GTS. You differentiate with respect to t and then s. All right, and then on the right will be d over ds, s minus 1, lambda s minus mu times g of s. Okay, and earlier we have an expansion, s minus 1 times lambda s minus mu, which was lambda s squared minus lambda plus mu times s plus mu. We have that earlier. So use the product rule to differentiate. You get s minus 1 times lambda s minus mu times gss, second derivative of g with respect to s, and then plus Well, you need to differentiate this term, which is 2 lambda times s minus lambda minus mu, okay, times gs. Okay, and now we set s equals 1. Setting s equals 1, what we have here. Setting s what we have here. Well, because mu of t is this expression, right? This tells us mu dot of t would be d squared g over dt ds, and then 1t. Yeah, because here you can just treat this as a single variable function in t, because s is now fixed, right? And now just differentiate with respect to t, and that's what we have. So setting s equals 1 on the left-hand side gives you exactly mu dot. On the left you have mu dot, and the first term cancels because s equals 1. And here, the second term just becomes, s equals 1, you got 2 lambda minus mu minus, 2 lambda minus lambda minus mu. This is lambda minus mu. But this is a very meaningful quantity. Lambda minus mu is the individual birth rate minus the individual death rate, and then times g of s. So g of s, actually, when gs, not g of s, but rather the first order partial derivative of g with respect to s, and then you set s equals 1, and that's exactly mu t. Oh no, I can't use mu because mu is already, you see, mu is a bad notation, you see. Let's just use m, that's okay. Let's change that, because mu is a death rate. Let me just change the notation, okay? I'm sorry. M of t. So m dot is lambda minus mu times m of t. Isn't that nice? Because that's the original Malthus model of population growth. So lambda minus mu is the net individual birth rate. The individual birth rate, this is individual birth rate minus the individual death rate. So that's the net individual birth rate. And that's actually how population dynamics on a macroscopic scale is modeled. So typically on a nation scale, you can say do the census and whatnot, and you calculate on an individual basis how many births per person, right? And on an individual basis, how many deaths on a per capita level, right? This is a birth rate. I mean, individual. This perhaps not very standard notation, but standard terminology. But basically, that's birth rate per capita minus death rate per capita. And now we just have this linear differential equation, the simplest ODE, simplest non-trivial ODE. The birth rate per capita and death rate per capita. All right, so this gives you the net growth rate, net growth rate per capita. And this recovers the classical Malthus model. The classical Malthus model is just this ODE. So of course, the solution would be, of course, equipped with the initial condition, right? Initial condition mu m of 0, right? M of 0 just expected value of x of 0, but x of 0 is a constant, which is n0. So m0, m of 0, just n0, okay? So together you have the evolution of the mean. M of t is immediately n naught times e to the lambda minus mu times t. Okay, so it says if the birth rate exceeds the death rate, then the average of x of t grows exponentially. Let's draw a picture for that. So x of t itself is a step function. X of t itself is a stochastic process, a step function, but its mean grows like a smooth function. Well, not like a, this mean is a smooth function like this. Use a dotted curve. This is a mean curve, mu of t, m of t, when on average you have more birth than death. That's very intuitive. And of course, in the opposite scenario, because in the opposite scenario you have exponential decay. This is m of t, where lambda is less than mu. Just gradually tend towards extinction. And in the critical case, where you have perfect balance between the birth rate and the death rate, the mean function stays constant. So this is m of t when lambda equals mu. And of course, the constant is n naught, the initial value. So that's the time evolution of the mean. The sample paths themselves, as I mentioned, remains a step function. So the sample paths are like this, and it goes up or down like that. Okay. This is a typical sample path, but on average, it evolves like the exponential function. I think this is interesting. Okay. So now we have this ODE for the time. We have this ODE for the mean, and it turns out that's a classic Malthus model. This is classic Malthusian. Is that how you pronounce it? I don't know. Malthusian. Growth or decay. Malthusian, aka exponential growth and decay. So you can, as you can see, the stochastic model, the linear birth and death process, can be seen as a stochastic analog or a generalization of the classic Malthus model. So you have, this is the assumption. That's why the Malthus is in the name. All right. Of course, the classic ODE is deterministic. Right? The classic ODE is deterministic. It will not describe, for example, extinction. That even in the case where you have a lambda less than mu, that is exponential decay, the exponential function never actually touches 0. It just tends to 0 indefinitely. So, of course, this is okay. This is okay on a macroscopic level. So let's say if the population that you model is of the magnitude of millions, then of course predicting the exact time of extinction is beyond the capability of this model. So you can safely just talk about say, for example, the average decays to a certain threshold, and you would consider it to be pretty much 0. However, that's not quite really a feasible choice if the population size itself is small. Okay, so let's say if you already have a small population and you really care about the time of extinction, then the mouse's model would not actually be very helpful. Right? Even let's say say the population of panda, right? You can calculate the birth rate and death rate per capita. But the mouse's model will actually never tell you when the population will go extinct. And that's actually very nicely captured by the stochastic model, and as we shall see, because right now we only have the ODEs at our disposal. Right? If you really want to get the probability of extinction, and equivalently, as we shall see, the distribution of the extinction time, you really need the function g itself, which has to be solved from the PDE. Okay, so now what we just did is deriving the ODE satisfied by the moment from the PDE. But to get the extinction probability and equivalently extinction time, you really need the big G itself. All right. So with that out of the way, let's just wrap up the derivation for the moment equation. That is, we want the variance too. So how does variance behave? Is that going to be intuitive? Well, our intuition is that if, let's say, lambda is greater than mu, then overall, because of the exponential growth, right? Overall, because of the exponential growth, the variance should also grow in time. So the sample curves becomes more spread out as time increases. So that's the natural intuition, right? And in the opposite case, where you have lambda less than mu, we predict that for in a short time period, that is when t is close to 1, in a short future, the variance is going to be small, well, simply because the trajectory don't have much time to deviate from the initial condition. That's our prediction. In a long time, however, because of extinction, because of the fact that the mean of t tends to 0, we expect the variance to be small in this region as well. So we expect that the variance would have a maximum value somewhere in the middle, okay, in the intermediate future. So that's the prediction. As for the critical case, we don't really know. Okay, I can't think of a good intuition for that, but let's see if that's really what's going to happen. So let's do the second moment. So you have the PDE, you have the definition for the second factorial moment. So what do? Well, we take the differentiation with respect to s again. So now you have d squared over ds squared PDE. And let's see what happens. Well, we already have the differentiation after the first order differentiation, right? So we would like to use this result. Okay, so here, from this thing, dts, we're just going to differentiate with respect to s on both sides and see what happens. So this is what we have so far. D over ds PDE gives this. Okay, and then we're going to take the positive with respect to s once again. Okay, does everything still make sense so far? I deliberately prioritize a probabilistic example because I know a lot of subscribers of the channel really subscribe for the stochastic and statistic stuff. Okay, this is typically not included in a standard introduction to PDE. That's why I didn't use Professor Avery's text, which is in the description, or Lieberman's text, which I recommended in the first stream. This is usually only introduced in a dedicated stochastic method text, and I think for physicists. So Yeah, this is I choose this because I know a lot of people subscribe and are interested in stochastic stuff. Um, Typically, you don't see this in intro PDE text. In this example in the notes, no, actually, no, it's not in the notes. It's my own notes. Okay, it's actually not in the notes. As I said, this is somewhat of a more rare, less well-known example of introductory PDE. This one is actually not in the notes. The traffic thing is in the Huberman's text, which I showed last time. Yeah, so last time we also derived the traffic thing. The traffic PDE is in the Huberman's text, okay, which I showed. So anyway, let's come back to this example here. So d over ds again will give you GTSS. And on the right, well, things are more complicated, so you have more things to differentiate. Here, you get s minus 1 times lambda s. I'll come back to book recommendation later, okay? Numerical method is also a very big topic. If you wanted to say specialize on which area of numerical, say numerical PDE or numerical linear algebra, you can say so in chat. I'll be more specific because I also have a lot to say about numerical analysis. All right, we'll finish this example. We'll finish deriving the moment equation, and we'll come back to chat questions. Okay. Yeah. So usually my chats are pretty quiet. Okay, that's usually what tends to be. I'm okay with, of course. I often go to JC Practice in Math, broader numerical method. Okay, got it. So I also go to actually he changed the channel's name called Math Can Be a Hobby. Actually, guys, I will link his channel here. So Math Can Be a Hobby YouTube channel run by JC. I don't know what his plan is, actually. I don't know. But he seemed to suggest today that more live streams are going to be on his second channel, actually his new channel, called, what's that? The new name, called Practicing Math Live. So it's a brand new channel. So go ahead and support him. I was saying, like, on his channel, on his lives, chats are actually much more active. Okay, his chats are much more active, perhaps because he shows his face and his cats. So instead of me just a whiteboard, okay, and a bunch of text on the screen. So perhaps that's the reason that his chat is more active. But then again, I would like to, I think this is already enough information going on the screen. If I put my face, that would be too much. And the thing is, I really want, that's really just an impossible goal. I'm saying that what I really wanted for my stream is to have kind of a university lecture halls style blackboard. Those big lecture halls with 4 pieces of blackboard at the front. Now, let me just show you an example of that. So university lecture halls. I think that would be the correct setup to do math in a seminar or lecture, university lecture hall with 4 blackboards, with like a sliding blackboard, but with 4 pieces. You guys have seen that? 4 pieces. I don't even know it has a dedicated name. I think that's the most convenient. I was a TA in a university, and I loved that lecture hall. Yeah, something like that, guys. I hope my screen can be like this. It will be so much easier for me to reference stuff. I don't have to scroll back and forth and say, oh, by this result. And, I want this kind of thing. That would be ideal. But if I have a very packed board and my face, on the screen, then it would just be unmanageable. I hope I can have this kind of setup, but I think it's difficult, and to be honest, it will be hard for, say, a mobile user to watch. So I just try to minimize digression and and that kind of stuff. You see, this is crazy. This is the best. This has 6 pieces. I hate lecture hall with a small blackboard. So you have to erase your what you've written over and over, and sometimes those results are needed to be reused. You know how it's like, right? You quote the equation that you derived earlier, and this is really the best format for any kind of math presentation. But yeah, this is the way it is. So as I was saying, like that's why I don't do face cams anymore. I mean, I used to have face cam on some of my old videos, but I figured this distracting. Okay. Anyway, so you really need to up your cat game. I know, right? Cats are the rulers of the internet. It helps the channel. I know. I'm not. Yeah. Anyway, so as I was saying, like here, differentiate the right hand side once again. So things are getting more complicated. Differentiate this. Remember here earlier, differentiating this gives you 2. Here, same expression here. 2 lambda s minus lambda minus mu. 2 lambda s minus lambda minus mu times oh, sorry, there should be a triple s subscript here, and this is just g double s. Okay, and then plus what's the differentiation? Yeah, so here you have differentiate this while keeping the same factors, keeping the front factor the same. You got to pick up a 2 factor here, and 2 lambda times gs here. Okay, yeah, this is what you get by differentiating it again. And now you set s equals 1. So setting s equals 1 now gives what? That's the left hand side is the okay. Let's call this m2. Okay, so let's call this m2. This is m2. m2t. Right. So the left hand side is now m2 dot. Yeah, m2 dot. That's the time derivative of the second factorial moment. Setting s equals 1 kills the first term. And the second term now reads 2 times lambda minus mu, right? And then times GSS evaluated at s equals 1. GSS as s here. GSS as s equals 1, that's just m2. So this is m2. Nice. First order linear. We like that. And the last term would be 2 lambda times, well, gs when s equals 1. Well, gs when s equals 1 is just mt, or the first order factorial moment. So that's mt, but that's already solved. So you can substitute that in. So this is just mt. All right, so this way you get what we call a first order linear inhomogeneous ODE. You really need to know your ODE before, like just basics of ODE. For example, first order linear, this is considered very basic ODE material before you dive into PDE. Now, I wrote a little post about prerequisites and whatnot on the channel during the weekend. So you go ahead and read that. But here we'll actually review how do you solve this. Okay, so by the way, let's substitute mt in there. Okay, m2t plus 2 lambda n naught e to the what's that? Lambda minus mu times t. Okay, so here we finished deriving the ODE. So this is the ODE for m2 of t, which is defined as the expected value of x of t times x of t minus 1. I hope the guy who asked about numerical analysis is still in chat. I apologize because I wanted to concentrate effort on deriving the differential equation. I apologize if you left the chat, but just for the record, what I recommend for a numerical method, if you're still there, snap, please let me know. Okay. Yeah, Snap asked about broader numerical method. So I'm going to recommend a series of texts on numerical analysis by very much the same author. Okay, so this is a little bit break from the main topic. I'll come back to the consequence of this in a bit. So what are the books? The first one, perhaps the most user-friendly one, is called Elementary Numerical Analysis by Atkinson and Hahn. So this is the one. Elementary Numerical Analysis by Atkinson and Hahn. Let me just see, give you what's the yeah, this is the cover. So yeah, actually you can already see what I'm going to recommend next. So this is the introductory textbook, and basically Atkinson and Hahn, they're dedicated numerical analysts. Okay, so this is a broader approach. Sorry, the broader introduction to numerical analysis, which I like a lot. It's very hands-on. Okay, it doesn't do super in-depth proofs. Okay, so basically numerical analysis can be approached in many ways. You can treat this as an engineering tool, as a mean to an end. Okay, although personally that's not my view. I understand this is a popular approach, so I'm not going to dispute that. If you just want to learn a bunch of recipes and say code them, or should be able to use a package, the numerical method packages fluently, it wouldn't be a terrible first thing to do if you just focus on algorithms. Okay. Although that being said, what you like to still pay attention to when it comes to numerical analysis, like especially a first introduction to numerical analysis, is even though you might not have the time or energy to spend on the proofs, try to pay attention to which method is appropriate for what task. Okay, because the most common mistakes when it comes to applying numerical method is to treat them as canned algorithms and just applying them indiscriminately. Okay, that would be a great mistake. For example, if you want to solve for a root, okay, for differentiable functions you can use Newton's method, but for non-differentiable functions you got to try something else. Say, for example, the secant method. Okay, these are technical methods in numerical analysis in the field of root finding. So pay attention to the assumptions of the method, even though you might not have the time energy to go through the proofs as a first study, and that's okay. Okay, so this would be my recommendation for beginners. For more advanced readers, I would recommend this book by the same author. It's called Theoretical Numerical Analysis. This is more at a grad level. Okay, this is more at a grad level. It covers more specialized topics, such as numerical methods for solving PDEs, integral equations, and whatnot. I think Atkinson and Hahn, their field was the field is the field they published research on, aside from generic more broader numerical analysis is on the numerical method for integral equations. So this is actually a great book. This is awesome if you're interested in the more advanced stuff. And if you're taking, say, applied functional analysis simultaneously, this gives you a great idea of how functional analysis is used. Because functional analysis is a big subject, and usually even in applied sort of courses, you don't have much time on actual application. This is a great testing ground, or proving ground, so to say, for what you learn in functional analysis, to see how things like norm space, Hilbert spaces, and the big theorems about, say, Sobolev spaces, etc., are used in practice. So these are my two recommendations, all right? By the same authors, Atkinson Han, Elementary Numerical Analysis for broader introduction, and this one, Theoretical Numerical Analysis for more proofy, more in-depth investigation, which is really, I think, just my personal opinion. I think if you're studying numerical analysis as an applied mathematician, this is the one that you should go for. This is the one you should go for. You should treat numerical analysis as a branch of analysis, along with real analysis, complex analysis, functional analysis. That's the appropriate positioning of the discipline. Okay, not a subfield of computer science, not a subfield of engineering, but a branch of analysis on its own. Okay, and the great advantage of doing so is that you will see things like Newton's method can be the main idea of, say, like Newton's method. Yeah, actually, this is a good picture for Newton's method. Just this page. This is a tangent method. That's Newton's method. So the idea of Newton's method can really be extended in an extremely wide range. You can use the idea of Newton's method to solve, say, things like nonlinear PDEs, and not just nonlinear algebraic equation, which I think that's where the functional analysis framework really shines, and it saves you effort for understanding different techniques. It gives you a unifying point of view, and this is a very modern point of view, which I firmly believe modern applied mathematicians should master. Okay, so enough of that. Let's come back to the main derivation. Now that was a nice break. Snap, you answered because the chat didn't scroll. Okay. Snap, yes, you could provide any prerequisites. No prerequisites. No. Numerical methods don't have any prerequisites. If you know calculus and linear algebra, I guess that's the prerequisite. Like, for example, numerical analysis, say you want to solve for roots, right? At least you should have an understanding of what root finding is about in algebra. Numerical analysis talk about numerical linear algebra. So the prerequisites are really self-evident. Okay, if you don't have experience with solving linear equations by hand, then I think it would be difficult for you to study numerical methods for linear system. Right? If you never calculated integral by hand, it would make little sense to learn how to calculate integral numerically, even though technically speaking these aren't strictly prerequisites of one another. Like, you can still learn how to evaluate integral without knowing the Newton-Leibniz formula. Right? That's still possible, but overall, introductory numerical analysis don't have a lot of prerequisites, if any. Okay, and in those cases, typically things are very self-evident. You don't need a bit of a programming experience would be nice to have, actually. So that's another non-mathematical prerequisite. Familiarity with at least one programming language would be beneficial. Even though numerical analysis in itself has nothing to do with programming. Okay, numerical analysis is a very earthly subject. It's as old as mathematics itself. Numerical methods were developed initially to speed up manual calculation, right? To solve quote-unquote unsolvable problems, the ones that has no analytic solution approximately. And this was for 1,000 years done by hand. And very much the giants, mathematicians in the early modern period, they're all numerical analysis. They were all numerical analysts. Newton was one. Well, we just talked about Newton's method. Gauss was one. Actually, Gauss's private notebook was not dominated by his proofs, okay, but rather calculations, manual calculations in celestial mechanics. Gauss was also a numerical analyst among many things. Euler, Laplace, they all did tremendous amount of manual calculations. So the point is, numerical analysis on its own has nothing to do with programming. It does very much has to do with algorithm. Okay, it doesn't very much has to do with the design and analysis of algorithms that is meant to study continuous problems discretely. Okay, so that's what numerical analysis really is about. It has to do with design and analysis of algorithms that is meant to approximately solve continuous problems. Okay, problems in the continuous mathematics. That's what numerical analysis is about. That being said, if you have prior exposure to at least one programming language, general purpose programming language, or more specialized programming languages for, say, applied mathematics, that would also work. Things like MATLAB, R, that's for statistician, but it would still work if you try to use it as a generic language for numerical analysis. So that would be my comment on the prerequisites. But overall, do not so to say. I'm trying to say is the prerequisites are usually the least problem. The least problem when it comes to entering the field of numerical analysis. It's usually when you started studying it, you will see why I make that comment. It's usually because of there's so many methods and so little insights. That's, in my opinion, the biggest problem in introduction to numerical analysis. You are given so many weapons. You are given a whole arsenal of method, and quite often the emphasis is on how to repeat the steps mechanically rather than which method you should use in whichever circumstances, in what circumstances. So that's usually the main difficult thing for introduction to numerical analysis. Like, for example, numerical ODE, the Runge-Kutta method. That's a family of methods. Introductory textbooks tend to give like 10 of them. And especially in more engineering-oriented textbooks, they give you like 10 Runge-Kutta methods. Well, which one should you choose? Right. So that's the thing. The prerequisites tends to be the least of your problems. All right. So would it be fair to say that derivatives computed by different software packages typically rely on numerical methods? I know Mathematica uses symbolic differentiation. Actually, symbolic differentiation and numerical differentiation are very different things. Okay, symbolic differentiation, or just say symbolic mathematics, symbolic calculation has actually a lot to do with abstract algebra rather than numerical analysis. Okay, so symbolic differentiation is used for saving manual derivations. Okay, derivations are like what we're doing here. Okay, so in principle, these can be done using a symbolic calculator. For example, in Python, you got the SymPy package that handles this sort of calculation. So we're probably not going to see any of that on the channel because this is the channel that focuses on the fundamentals, not technology. I'm not a technophobe, but just I don't want to introduce this extra cognitive layer. Okay, I want to do differentiations manually, so everything stays focused on the principle of mathematics itself rather than technology. But again, symbolic differentiation is usually how, for example, the derivatives are calculated in machine learning. Because in machine learning, you got this objective function or cost functions of just thousands, if not tens of thousands of parameters. Okay, so it's like calculating a giant Jacobian. Yeah, that's pretty much what so to say machine learning training method relies on. You need expressions, analytic expressions for massive Jacobians, and these are usually done by symbolic differentiation, but not numerical differentiation. Okay, so just to give you an example. So we all know x squared derivative is 2x. Right. So symbolic differentiation will actually return this formula exactly, whereas numerical differentiation will give you an approximation of this. So numerical differentiation essentially is that, say, if you're interested in the slope, approximate slope at x equals 1. So numerical differentiation will actually gives you, okay, this is approximately, say, 1.1 squared minus 1 squared, okay, minus 1.1 minus 1. So this is what numerical differentiation does essentially. But symbolic differentiation will actually give you the expression. Yeah. So that's very different. Okay, I just want to make that distinction super clear. Symbolic differentiation or symbolic mathematics is different from numerical mathematics. These are two separate fields. And once again, if we say go to if you do the symbolic integration in Wolfram Alpha or whichever package, Mathematica, Maple, or SymPy, once again the technology don't matter. The actual theory that support these methods are more to do with abstract algebra rather than with numerical methods. Okay, there's a different field. Okay, so now let's come back to the variance differential equation. Right? We derive the variance differential equation, which we reiterate as following. Okay, let me just remove that t because that's a redundant thing. So that would be m2 dot equals constant 2 lambda minus mu times m2, and then plus 2 lambda n naught e to the lambda minus mu t. Okay, this is derived from the PDE, even though itself is an ODE. So how do we solve this to get the dynamics for the variance? Actually, yeah, why don't we just get the dynamics for the variance? We don't want to solve this and then, I mean, I think both is okay. You can, both method is okay. I think you can. Why don't we just derive the ODE for the variance? Let's derive the ODE for the variance. What is ODE? What is the ODE for the variance? Which is sigma square of t, defined as the variance of x of t. And what is the variance of t? Variance of x of t is, let's write it as the expectation. That's the most commonly used formula in statistics. The second moment minus the first moment squared. Right? So we have these at our disposal, or equivalent, or enough information to get these. Right. So the second moment, as we said earlier, can be recovered from the factorial moment. Expected value x squared is m1 plus m2. Sorry, that's bad. Oh no, that's actually not bad. That's correct. That's correct. So expected value of x squared is here m1 plus m2. That's m1 plus m2 and minus here minus xt. Is that right? Oh, sorry, that's not correct. Should be subtract the expected value of xt squared, so the minus m1 squared. So that's sigma squared, the differential equation for sigma squared. Okay, so that's sigma squared, not differential equation. So as a result, m2 is what? M2 is sigma squared plus m1 squared, yeah, minus m1. Just to double check. Yeah, that looks about right. M2 is sigma squared plus m1 squared minus m1. So this tells us that m2 dot here, right, m2 dot is sigma squared dot, okay, sigma, just say d sigma squared over dt, and then plus here you have d m1 squared over dt minus m1 dot. M1 dot, all right? And also the right-hand side of the d, which is 2 lambda minus mu times m2 plus 2 lambda m1, m equals m1, okay? M equals m1, so here I'm looking at this expression here, 2 times lambda minus mu times m2 plus 2 lambda m1. Let's do the substitution, which is 2 lambda minus mu times sigma squared plus m1 squared minus m1, and then plus 2 lambda m1. So let's simplify that. This gives you 2, because m1 is already solved, right? So right now the only unknown is sigma squared. You just want to get a differential equation for sigma squared. 2 times lambda minus mu sigma squared plus 2 lambda minus mu together times m1 squared minus m1, and then plus 2 lambda m1. Okay. So that's the right hand side. Is that m2 dot equals this thing. Okay, equals this thing. So set them up together. M2 dot equals that. So you get d sigma squared over dt plus dm1 squared over dt minus m1 dot, right, that's the left hand side, equals this. Okay, equals this. All right, so let's collect the m1 terms and simplify. So here we go. We have it's not super obvious, right? It's not okay. So anyway, so here you should get d sigma squared over dt equals 2 lambda minus mu sigma squared okay, let's do some simplification here. You have 2 lambda minus mu m1 squared minus 2 lambda minus mu times m1 plus 2 lambda m1 minus dm1 squared over dt plus m1 dot. Okay, so simplify this mess. The point is, this is a solved function. This is not unknown. So even though this looks kind of ugly, it shouldn't be a problem. So first of all, m1 dot, remember m1 dot, the differential equation for m1 says m1 dot, right here, is lambda minus mu times m1. So this will just give you, this cancels out with lambda minus mu times m1. Remove the 2 factor. Okay, m1 squared minus lambda minus mu times m1. m1 dot goes away. All right, and then plus 2 lambda m1 minus dm1 squared over dt. All right, so let's do the substitution, shall we? So here you have 2 lambda minus mu times m1 squared. m1 squared, as mentioned, is n naught squared times e to the 2, here, m1 is here. So it's n naught squared times e to the 2 lambda minus mu quantity t. Okay, I know this is a little bit messy. Okay, just be a little bit patient. We should be able to solve this no issue. And you have 2 lambda, actually 2 lambda minus lambda plus mu. This will give you lambda plus mu times m1. Lambda plus mu times m1, all right? And then minus d over dt of m2. So this d over dt, m1 squared. m1 squared, we just have this here. So that's m1 squared. So, because these are all exponential functions, I don't think this should be too ugly. The final result shouldn't be too ugly. All right. All right. So, hold on a second. Okay, this looks okay. So here you have 2 lambda minus mu times n naught squared e to the 2 lambda minus mu t plus lambda plus mu times n naught e to the lambda minus mu. Okay, e to the lambda minus mu. What's that? Quantity t. Yeah, that's m1. That's m1. So now differentiate with respect to t. You got n naught squared times 2 lambda minus mu e to the 2 lambda minus mu quantity t. Quantity times t. All right. So let's simplify it. Does it look like these two terms actually cancels? It does, right? Isn't that fantastic? If that's really true, I just want to make sure. So actually they do cancel. So you just end up with the middle term here. Okay, so that's cool. That's cool. That's very much welcome. Okay, so you just get lambda plus mu. Lambda plus mu times n naught e to the lambda minus mu t. Okay, so that's this part right here. It's now simplified to this term. All right. Oh, sorry, I forgot. This is nonsense. This should be sigma squared. And actually, you know what? Let's take a look at a special case. If, say, lambda is mu. Let's look at a special case, shall we? The special case actually is very interesting. It says sigma squared would grow linearly. So here, the special case says when lambda equals mu, you would have d sigma squared over dt. Here, the right-hand side in the first term cancels, and the term that trails behind it, which we just derived, is just lambda plus mu. Actually, it's because they're the same, so it goes, they just call them beta, all right? Now, say if they're the same, say the common value is beta, then you just get 2 beta times n naught constant, i.e. sigma squared grows linearly, like a Brownian motion, out of all things. Remember, I mean, if you guys have watched the stochastic series, stochastic calculus series, the fundamental characteristics of Brownian motion is that it is a continuous time stochastic process that takes continuous values, that for any time interval, during any time interval, the variance is linear. The variance is linear in time. Here we have a similar situation. Even though here the stochastic process itself is non-negative integer valued. This is very cool. Okay, did not expect that at all. Okay, so overall, the ODE for sigma squared as a function of t is now determined. So let's still take a look at the general case. So it's like here, I'm saying is for the middle case, where lambda equals mu, you would actually see a roughly, no, it's not linear spread, but rather, because sigma squared grows linearly, right? Sigma squared grows linear, that means sigma itself grows like a square root of t. Right? So which is equivalent to saying that sigma is proportional to the square root of t. So here in the middle portion, you would see the spread. The spread is roughly like this. Maybe I should draw it this way too, and then squeeze it. I know. Sorry about that. So I'm saying is, yeah, that's approximately the bound that controls the spread of the middle case, the critical case. Come on. I really hate this. Can I just select this piece of curve here? All right, thank you very much for allowing me to do so. Yeah, so that would be the spread in the critical case. And of course, also by symmetry, I can't do that? Huh. Can I flip it? Rotate? Yeah, flip vertically. Nice. Yeah, so this is a spread of the critical case. Right. So the point is, because of the square root dependency, the spread quickly grows in the initial phase. The square root function grows rather quickly. The slope is infinite, in fact, near the origin. Whereas for large t, the slope is rather small. It grows slowly. So the point is, the rate at which uncertainty grows in the short time is actually quite large. So that's kind of an interesting observation here. All right, so let me just write down the full ODE in the general case. D sigma squared over dt is here 2 lambda minus mu times sigma squared plus the inhomogeneous term, or the forcing term, which is lambda plus mu times n naught e to the lambda minus mu t. All right. And what would be the initial condition? Initial condition, well, since we're treating initial state as perfectly given, so that would be 0. Sigma squared at time equals 0 would be 0. So that's our setup, the original setup. So we assume that the initial population is determined, is known. All right. So that's the ODE for the variance. And now let's solve the variance ODE. To do so, there are multiple ways of doing it. Right. The most common way of doing so would be the so-called the method of variation of parameters. That is to say, you first ignore the inhomogeneous term. So you focus on the what we call the homogeneous DE. Now, associated is the solution. Okay, the associated homogeneous DE hang on, is d square d sigma square over dt equals 2 lambda minus mu sigma squared, which of course this is an exponential model. So sigma squared equals constant. Now c is a integration constant of integration times e to the 2 lambda minus mu t. Okay, and then we're going to use the so-called method of variation of parameters. Variation of parameters says if we replace the integration constant c by a function, an unknown function that depends on t, then we can substitute the trial solution, into the original ODE and get a relation for c. Oh, hi, Levi. Thank you very much for joining the stream. So the variation of parameter method says now you're going to use a trial solution based on the form of the solution to the homogeneous ODE. Doing great, thank you very much. So this is a trial solution. Sigma square of t is c of t times e to the 2 lambda minus mu t. All right, and then we're going to substitute this into the ODE and get a relation for c. Okay, c is unknown. And this method works for higher order linear differential equation as well. So it's pretty cool. So it's pretty nice. I think originally due to Lagrange in his work on celestial mechanics, on perturbation theory of celestial mechanics. So this is quite an ingenious method. Let's substitute that in and see what happens. So on the left hand side, because now c is a function of t, you need the product rule. So that's c prime of t times e to the 2 lambda minus mu times t. Plus, here what we have here is c of t times e to the 2 lambda minus mu times t times 2 lambda minus mu, because you're differentiating this exponential function. All right, on the right hand side would be 2 lambda minus mu times sigma squared, which is ct e to the 2 lambda minus mu t plus the extra term lambda plus mu n naught e to the lambda minus mu times t. And guess what? A nice cancellation happens. This term and this term cancels out. All right. So as a result, c prime is now available. C prime of t, is lambda plus mu times n naught e to the minus lambda minus mu quantity times t. Okay. Of course, here we're assuming that lambda and mu are not the same. Okay, because the special case are already solved. So from now on, assume you have lambda not equals mu. Okay, assume that's not the case. Okay, and now you can integrate this to get c. C of t after integration would be what? Would be here lambda plus mu over lambda minus mu and naught. There should be a minus sign up here. E to the minus lambda minus mu quantity times t, and then plus a new constant, let's say d. Okay, just to check everything if everything still makes sense. Oh my goodness, Levi, I'm sorry, I still haven't talked about the geometry channel. Yeah, I'll make a post, okay? I promise. My goodness, I'm so sorry. I didn't try to ignore you, but yeah, I'll promote the geometry channel. And actually, you know what? I'll do it here, okay? I'm sorry. So this is something I really wanted to spend time on, but it's just I never really have the time, which is a shame. It's on Euclidean geometry, because when I first learned geometry in high school, it was such a mix of, you know, traditional Euclidean geometry and coordinate geometry. Because I think what we did in high school is that we introduced the Euclidean way, but not serious enough to actually do practice in it. And then immediately we transition to coordinate geometry. But here, this is Olympia Geometry Club. I think it features the geometry problem actually from IMO. I wouldn't be able to solve any of them. I mean, to be honest, I wasn't super interested in just competition, but I was interested in Euclidean geometry. However, our textbook simply did not spend much time on them. Okay, so yeah, guys, if you're interested in classical Euclidean geometry and challenging problems, go check this guy out. See, over 300 videos, well over 300 videos, purely on Euclidean geometry. Yeah, I wish I have more time to actually seriously study Euclidean geometry. You can see there are super cool problems. Just look at these diagrams, man. I know it sounds very superficial, but I hope one day I'll be able to study some of the classic. You see, I never heard of this theorem. It's called Steiner's theorem. It's so cool, man. It's like hidden treasure. It's like what is called it's like what is it called, forgotten skill or something. Yeah, to do the Euclidean geometry a la Euclid. Yeah. So guys, if you're interested in classical Euclidean geometry and you're interested in IMO and just challenging problems in geometry, go check this out. Oh, actually, this one is Chinese. This one is from a ancient Chinese text. I didn't even know that. Measure of, yeah, this is, Chinese geodesy. Wow, pretty cool. Is this guy actually Chinese? This is very, wow, this, yeah, so, oh, hi, Leo. Welcome back. I mean, sorry, I didn't mean to, like, I'm sorry. Perhaps I wasn't being super clear and I rubbed people the wrong way. I hope. I don't hope, but perhaps that was what happened. So Leo is talking about this post I wrote when it comes to prerequisites, right? And I think category theory also is very appropriate because you don't need any formal prerequisite to start learning category theory. Logically speaking, it is independent of anything. Logically speaking, it doesn't even depend on set theory, right? But as one guy put it perfectly here in chat, Guy Pirate says the analysis. The guy analysis said it's like you need very little to learn the basics of category theory, but you need a lot to get category theory. Right? This is even more so than topology. So topology is basically abstract analysis. At least point set topology is concerned. You can think of it as abstract analysis. Or at least the original motivation is to do abstract analysis, but then it later on became a subject on its own. right? So the point is, Moncrief is saying is you can study topology without a formal background analysis and then deduce analysis as a special case, right? So logically, that's a perfectly valid development, and actually, that's the original motivation for topology, is to keep only the bare minimum needed in, say, discussing continuity, right? But the problem is, if you have no background analysis whatsoever, it's very difficult to build intuition, and it's very difficult to get a sense of where the series is heading. So that's a great paradox of math learning in general, because math is different from so many different subjects, including fellow STEM subjects, is that math don't usually begin from the fundamentals. Historically and contemporarily, what usually happens is you have these interesting problems that needs to be solved, and the current technology, the current machinery, the theory, and whatever aren't rich enough for that. So you decided to dig deeper. You want to consider the general situation, right? So the fundamentals are usually a result of concrete problem solving, right? But once again, because they are general, right, they don't presume, they aren't based on any particular theory or problem, right? Logically speaking, it can be studied on its own, but it's just, as a pedagogical experience, it is very difficult. It's very dry, and it's very unmotivated. So one guy actually, in the same comment section, one guy asked me to read and explain the first chapter of Bourbaki, the set theory volume. I was like, sure, because I figured, why not, right? I mean, we feature Russian-style mathematics on the channel. I think it would be fair to look at, say, French, because French is also very strong when it comes to mathematics. And well, back then, before the Nazis destroyed Göttingen, right? Before the Nazis destroyed Göttingen, France and Germany was on equal caliber. But then Germany was pretty much left in the dust after what Nazis did. And a lot of German mathematicians immigrated to not France, but the US, which largely contributed to the rise of US as the post-war mathematics superpower. Places like the Courant Institute at New York University. Right? Courant Institute was, well, named after Courant. Courant was a student of Hilbert, and he luckily managed to escape. So anyway, I was saying, like, you see, if you try to read Bourbaki, the first volume, technically you don't need background. Right? Technically, you don't need prerequisite to do so. It's just super hard and super, well, I don't know. It's just, for me, if I don't have the maturity that I gained from perhaps the entirety of undergraduate study, I wouldn't be able to sit through a single section. It's just that bad. Actually, I don't know. Like, I think, even though, I mean, I'm definitely not a Bourbakian, and I don't subscribe to their philosophy, or at least, very least, I don't subscribe to their philosophy of presenting mathematics. Okay, let's just put it as accurately as possible. I don't subscribe to their philosophy of presenting mathematics as this super abstract, super axiomatic, very little motivation, little to no examples. I don't subscribe to that, but I think it's we should give it a fair trial on the channel to see what reading it is like. And if you really want to study it, I mean, I'm not saying like I'm giving the right way, but just giving my honest attempt at it, so to say. I never read the test theory volume. I never did. I tried to read the single variable calculus volume, and it was painful. And it was super, super painful, even, well, with my current skill set. Okay, so I'm just gonna put it that way. Okay, so enough of that. Let's read some chat and continue the derivation. Yeah, so Leo is saying, because there's a myth like, aha, these goofy little shapes, which partially yes, but the reason those goofy little shapes come up is that the phenomenon is continuous, and often you just need a topological obstruction. Yes, exactly. exactly. I mean, there's TDA, which forgot in the moment. Yeah, the topological data analysis is also, I don't know if I'm going to attempt it because some people has requested it, okay? But I think for now, my background is very weak. But once again, I said it in my own post and whatnot. You can you should put your fear of lacking prerequisites aside. So I should really follow my advice, okay? And perhaps do a live on that. I just need to find appropriate materials so that I have at least a chance of getting to know what it's about. Okay, TDA. Once again, I heard that TDA, topological data analysis, is very powerful in cloud physics, in statistics of weather prediction. So, I mean, once again, I can't comment much on that. I'm not even a beginner. Okay, I never began. Okay, in that field, but TDA, there's a lot of interest in that. It is application of algebraic topology, which, well, I don't even have much background in algebra, so that's why I was saying, oh, Leo, you could teach me some group theory, right? And perhaps we'll do some. I mean, I'll at my own pace, I'll do some TDA and show it on live. I don't know about subscribing to Bourbaki, but I do. Yeah, that's true. Yeah, go ahead and subscribing, liking, and commenting on Leo lecture. Yeah, got promoted to Modern. Highly recommend it. Yes, calculated some homology groups for Simplicio. For Simplicio, I have no idea what that is. Simplicio complexes would be a good warm-up to TDA in case you ever want to go that route. I mean, I'm not sure if I should commit. Okay, I don't know. I don't even know if I should commit into that field. But it would be certainly it's certainly a good idea to be able to at least know the main intuition, right? Because the main intuition and what are the prerequisites to do that. I think actually this upcoming Saturday stream would be on information geometry. I'm still very, very far from being an expert in that, but at least I know enough, say, statistics and differential geometry to at least outline what would be the main idea, right? So that's the idea. So I hope to give a reasonable introduction to the main idea of differential geometry, not differential geometry, information geometry, and then spend the rest of the half of the stream doing the fundamentals. Okay, once again, without assuming a ton of differential geometry. Yeah, it's not a request. I know, but it's not a request from you. There are a request, and once again, I mean, this is my channel. I can feel free to pick whichever request I feel suitable. But the thing is, it would be hypocritical to preach, oh, you should challenge yourself, you should not give up on a regular basis while being afraid of trying new things myself, right? So there's that, right? Okay. It's such an easy thing to let other people, to tell other people to keep learning. End quote. This is a quote from, guys, I think this is a quote that deserves to be widely circulated by Math with Ming. It is such an easy thing to tell others to not give up and in learning. Or I should probably formulate this in a better way, but you guys know what I mean. So yeah, you're interested in doing PDE research in mathematical physics, which is great, which is awesome. You can spend your whole life on it. Yeah. Leo teaching main group theory does sound like a fun stream. Yeah, you know what, Leo? You should do something like this because I'm never afraid of being cringe. You should assign exercise on the spot and I'll try to solve it. If I can, then I can. If I can't, then say, if you leave me 10 minutes, I'll do this kind of think out loud method. And I'll try to get an idea. If I can't do that, You say, okay, Ming, time's up, 15 minutes is up, you failed, okay, I'll show you how it's done. Then do it, okay? I would like to show this process. I mean, if that's not something that you're interested in, let's say if we're doing, just for the sake of argument, okay, a group theory stream, let's say Leo teaching Ming group theory, okay, and Leo going to give the definition, perhaps an example, and say, okay, this is a little property you should prove as an exercise, and then the stream would be just going to be me attempting to solve that exercise. Okay, you don't need to like worry about, oh, what if this makes Ming look stupid or something. No, I don't care. That's the whole point, right? I make mistake all the time on my own stream. Like, I'm not afraid to say, okay, I don't know this, so I'm gonna BS around. No, this is, I think, excellent teaching and learning opportunity. If you're interested in that, I'm totally open to it. No, just basic group theory. Kraken. I'm just thinking about basic group theory because I never really learned it systematically. Oh, Levi's channel. Levi, send your channel in my Discord if you want to. Group theory and ring theory for now. Yeah. Well, yeah. So like, go ahead if you want to promote your channel and whatnot. Like, of course, I'm going to take a look at your material, like see, like just learn some baseline of expectation, right? I'm not going to just promote any channel, but still, like, chances are, if you show me what you do, like, we have a good chance of like, so to say, promoting each other's work. I hope so. Not on channel, but real life. Oh, wow. Okay, great, awesome. That's really awesome. So you're a professor or instructor, or at least a associate professor, lecturer, some kind of a real world teaching position. Is that what you're doing? I mean, Levi, I would love to put you on as a mod. I don't know if there's a maximum number of mod, but once again, I don't want people like come into the chat and see everyone's a mod. And anyway, so okay, let's come back to finishing up the derivation for the variance. Okay, so this is C of t, as I was saying. This is C of t, so sigma squared of t now has a general solution. C of t is now solved. Okay, so here you have minus, just this expression times the other exponential factor here, the other exponential factor, which is e to the 2 lambda minus mu times t. Okay, so to find d, let's use initial condition. So initial condition says sigma square of 0 is 0. So this gives you 0 equals minus lambda plus mu over lambda minus mu times n naught plus d. Right. So d is now determined, which is lambda plus mu over lambda minus mu times n naught. All right. So this says sigma square of t is d basically is a d is a constant, but we don't know its sign. Actually, we don't know the sign of it. But hopefully this function is all non-negative because that's sigma square we're talking about. Hopefully this is valid. Oh. So here you got lambda plus mu over lambda minus mu. So this expression sigma squared needs to be non-negative for all three cases. Now, all three cases we said earlier, lambda greater than mu, lambda equals mu, and lambda minus mu. Okay, so here we're only considering lambda not equal mu. So the thing is, we need to check whether this is always non-negative when lambda not equal mu. So that's something to keep in mind of. All right, times n naught, and then times minus, okay, inside you got minus e to the lambda minus mu t, and then times, actually I'm just going to borrow one factor of e to the lambda minus mu t. Okay, sorry, this would be minus and then plus e to the lambda minus mu times t. Okay, use a square bracket. Okay. And then times, what's that? E to the lambda minus mu times t. Okay, so let's check the sign of this thing. Oh, MTA. Okay, great, awesome. Levi, that's awesome. Using the book references prepared for notes. Okay. Oh wow. Levi, I guess I have much to learn from you. I'm pretty sure I have much to learn from you. You want to focus on research and seeing what can do about it. Well, it's not. I would say I strongly would recommend you see this through a different way. That teaching is a great way to improve your own fundamentals. At least that was my experience. So, well, we had teaching duties as mandatory duties, well, in the grad school, which I found annoying as a grad student, because in engineering you have the option. In engineering department you have the option to choose between TAing and not TAing. That's an option. And your financial support isn't hinged on that. But in math department we have to teach as TAs. So I had to do it. In retrospect, this was actually a great experience. But at the time I hated it. I just figured it was such a thing that that distracts me. Right? But the thing is, I think Terence Tao said, even when you just go full in on research, it's usually still a good idea to have some quote-unquote distraction along the side, because he spent a period of time of his life just doing nothing but research, but actually the output wasn't great. So yeah, it can definitely synergize with your research and just overall command of math, I believe. So anyway, coming back to this expression, is this always non-negative? So let's think about it, all right? So when lambda is less than mu, yeah, lambda is less than mu, then we would have a negative at the bottom and also a negative up here. Of course, when lambda is positive, because exponential will be greater than 1, then it's a positive. So this is great. This is awesome. All right, this is what we wanted. So as I was saying, that's the time evolution of the variance. The time of evolution of the variance is interesting because it also have different cases. When lambda is greater than mu, discussion. When lambda is greater than mu, then the exponential function is always greater than 1. Is always greater than 1. So, yeah, discussion. So here, first case, if lambda is greater than mu, then we have e to the lambda minus mu of t. Okay, sure, fair enough. Yeah, fair enough. Yeah. Okay, I feel you, Levi. Yeah, so yeah, because I mean now I have the luxury of saying, oh, it actually synergized. But then again, you have time pressure, you have publication deadlines, and then it's a different story, right? So this is greater or equal to 1 for all t, greater or equal to 0. Then you see, because of this is the quadratic function, so think of the quadratic function phi of t equals t minus 1 plus t times t, minus 1 plus t times t. Then the function looks like this. That's 2, 0, 0, and 1, and it's a quadratic function. My point is, when lambda greater than t, then this exponential function strictly is not strictly, but greater or equal to 1. So you're entirely on the positive, the positive and also increasing arc of the quadratic function. And this tells us that sigma square of t increases. And also second, when lambda is less than mu, in which case the e to the lambda minus mu times t would be between 0 and 1. So it's like this portion of the quadratic function. So as you can see, there is a maximum somewhere. This is maximum somewhere. So lambda t, not lambda t, but sigma square of t, it would increase and then decrease and tends to 0. The sigma square of t would increase. Let me draw a qualitative sketch. Sigma square of t would have this behavior. It will first increase and then decrease, and then tends, as it decreases, it tends to 0. There is a sigma maximum in the middle, sigma square max in the middle. And this happens when the quadratic function here, the argument takes 1/2. So sigma square max equals the factor lambda plus mu over, hang on a second, where does the square term go? That's odd. That's odd. What did I do? What did I do wrong? Oh, actually, never mind. This should be correct. But sorry, I think I made a mistake somewhere, because the dimension is messed up. The physical dimension is messed up. Sigma squared should be whichever unit of the population squared. Did I make a mistake here? Did I make a mistake here? Hang on, what's the unit of lambda and mu? Sorry guys, I think I made a mistake about the unit, huh? Here, going back to the definition of lambda. So lambda n should have the dimension of inverse of time. Lambda n should have the dimension of inverse of time. Let's assume n has no unit, so lambda has a dimension of inverse of time, so does mu. Okay, and going back here, what would be the dimension, say, yeah, in a super special case? Yeah, this is correct. Is it though? Is it though? Actually, never mind. It should be okay. It should be okay here. Going back in this derivation, the square term goes away. And the square term, I was just a little bit suspicious, all right? I'm just a little bit suspicious, but I think this is overall. Should I double check this? Maybe I should. Yeah, no worries. Thank you, Christian, for stopping by and for modding. Okay, I think I got the quality of the picture right. So let's just continue with this derivation. I think this is correct. N naught, N naught, and then times 1/4. 1/4. So this is the maximum of this would be 1/4. Actually, that would be mu minus lambda. Mu minus lambda to make it positive. Mu minus lambda. So that's the maximum spread. Right? That's the maximum spread, and it happens when e to the lambda minus mu times t equals 1/2. That is equivalent of saying t equals the natural log of 2 over mu minus lambda. So this is the time when the uncertainty is maximized. All right. So if we go back to the picture here, what qualitatively should happen is that for the first case, you just have this this monotone increase in the spread. The uncertainty gets bigger and bigger, in fact, unbounded as time evolves. But here in the decaying case, what would happen is you would get this behavior. You will get this behavior. So initially, let me just change the color to, say, blue, navy blue, not light blue. So the spread grows initially and then decays. Like this. Here, this is a time where the spread is maximized, which is t equals the natural log of 2 over mu minus lambda. Here you have the sigma max. This corresponds to the sigma max. Okay, so that's the moment equations derived from the PDE, right? So we still haven't talked about how do you solve the PDE, but my point is sometimes you can just get information from the differential equation itself, right? If you guys have seen some ODE, and this is also quite important, you don't always need to dive in and solve the differential equation exactly. You can also just extract information from the model itself. So where we're now, I think right now the only thing that is left to be done is the extinction probability, for which we really need the solution. So why don't we continue with the general PDE? Okay, so let's come back to step aside from the model and study how to solve first order PDE in general. Okay. Once again, this is perhaps a little bit different compared to a typical introduction on PDE. Typical introduction PDE generally start from, well, this is the general form, and here's the method, solve a bunch of PDEs, and you move on. Maybe you'll see an example, maybe you don't. But I would like to keep things grounded in concrete models, and then introduce major theory when I see it as appropriate. Okay. Okay. So now we're left with our final goal, the crown jewel. We're left with the extinction probability. We want P0 of t, which is G0 of t. We really want that. So, but for that you need G, i.e. you need to actually solve the PDE. So let's see, how can we solve PDE in general? So now we're going to the PDE general theory. Okay. So first of all, just some terminologies. definition, the order of a PDE is the order of the highest derivative, highest or partial derivative. Typically, it's the partial derivative. Actually, guys, I'm very hungry right now because I skipped dinner today. I should probably eat something, but let's just continue doing math for now. Okay, the highest derivative, the order of the highest derivative appears in the equation. Okay, so in general, okay, say for example, the most general first order linear not linear, but just first order PDE. It doesn't have to be linear, okay? First order PDE for u x of y as an unknown function is some function, say big F, which may depend on x and y explicitly, and of course u and ux, uy equals 0. Okay? So that's the most general form for the first order PDE. Okay, and the most general form for the second order PDE would be what? The most general second order PDE for the same format. Okay, two unknowns. It's easy to generalize to functions with arbitrary number of unknowns, but the notation would be more involved. Okay, so you will see the most general form, okay, with arbitrary number of variables in, for example, Evans's PDE. And now we're just going to keep things more manageable. Two unknowns, okay? Yeah. So yeah, bye, Levi. Thank you very much for stopping by. So yeah, this is x, y, u, ux, uy. Gosh dang it, I'm really starving right now. Okay, hopefully I can survive another hour. That's the goal anyway. All right, so that's the most general second order PDE. Okay, and you get to see the general pattern here. Okay, and definition, what would be linear or nonlinear? The PDE is linear if big F here, big F above is a linear function of u and all of its partial derivatives. Yeah, is hot. Hot, do you mean your favorite course in applied math 28 years ago was PDE? If so, great choice. I mean, it was definitely one of the highlights of my experience as an applied math major. It's glorious. So let's take a look at some examples. More examples. Yeah, wave equation, heat equation, Laplace equation. So these are the prototypes which we aim to also cover. So in both Western style and Russian style. So that will be ideal actually. du dx equals y e to the 5x. Right? This is first order linear. Right? Just like in ODE, just like in the study of ODE, typically when you approach a PDE problem, you try to classify it in some way. Although, that being said, it must be emphasized that the classification scheme in PDE is only a guideline. It is only a guideline, and the classification scheme itself is very incomplete, which is also part of the reason why this is such a difficult topic. So the second example is u triple x and then cosine of y times uxy plus x squared y squared uy equals x squared times u. So what would be the classification of this? Well, first of all, you got the third order derivative, so that's a third order. And notice that all the terms, u and the partial derivative of u only appears in a linear manner. See, so that's also linear. It's a third order linear. Okay. Next one, you got d squared u over dx dy, which is 8x plus sine of y. That's a linear PDE as well. This is a second order. Okay. Next up, so these are rather artificial examples, if I'm being honest. There's way more exciting examples than these ones, which are kind of contrived. But for just practicing the definitions, this is sufficient. Okay, I don't want to introduce too many. I don't want to drop too many terms. Okay, I don't want to drop too many names. If I give this example, like full of big names in physics, I think it will actually be more distracting than actually clarifying things. I just wanted to, right now, the focus is on spotting the right type or applying the terminologies appropriately. Okay, so I apologize for the lack of interpretation for these examples. All right, so here, what's the order here? Well, third order because of phi t. And actually, you can infer what's the unknown function. The unknown function is phi of txy. Right? There might be more independent variables, but because they do not show up in the PDE, you might as well just treat the independent variables as these three. Okay, so, well, this is a third order as mentioned, and it's nonlinear because of the product. Right? Because of the product, the function is not linear in its derivative, in the derivative of phi. So it's nonlinear. Now, as you can probably tell, nonlinear PDEs are in general much more difficult as a rule, okay, than linear PDE. And quite unfortunately, many interesting PDEs are nonlinear, even in rather basic phenomena, simple phenomena. For example, the traffic flow PDE we derived last time is nonlinear. It's called quasi-linear. So the function is still linear in the derivatives. So the derivatives still appear as linear terms. So that's why it's called quasi-linear. But it's still nonlinear. So this is a first order nonlinear. We got these examples, okay? Hi Johnny. Okay, so there we go. Let's first take a look at some rather simple PDEs. For example, the one I just wrote. How do you solve that? Example 5.3, how do you solve that? Well, because only the derivative with respect to x is involved, you can treat y as a constant. And you can just integrate with respect to x. So 5.3 is solve du over dx equals y times e to the 5x. Okay, we're starting things in a very gentle way, because I figure the birth and death process example is a little bit difficult. So let's just do things slowly, making baby steps one at a time. So the solution here is rather trivial because you can just integrate with respect to x. So integrated with respect to x gives us u as a function of x and y. Right? You treat y as fixed, so that's just 1/5 times y e to the 5x. And of course you need an integration constant. But what is the constant in this case? So this is a little bit, I mean, it's not difficult, but needs to pay a little bit of attention there. So in the ODE case, you just, without thinking, can write plus c. But here, because y is treated as a constant, whichever constant you put at the end could still potentially be a function in y. Because y is treated as a constant. Because another way to see this is, let's say if you substitute this expression into the PDE and see if it still makes sense. And indeed it does, because if you take the partial with respect to x, c of y just automatically disappears. This is an arbitrary function in y. Right? If you partial differentiate with respect to x, cy has no business here. It just vanished. So usually what we write is, we say the general solution includes an arbitrary function in y. Right? Literally any function. Doesn't even need to be differentiable. Anything, right? So this is the integration constant. Integration constant, and it's a constant in x. Did I? Oh, the book by. Okay, interesting. I'll just because in case I forget, I'll keep the book recommendations by chat recorded. Oh, this is a dedicated book on nonlinear PDE. Awesome. Awesome. I loved it. Okay, I'll go check this out. Awesome. What are the content? Your linear, first order quasi-linear, method characteristic. Oh, that's great. That's great. Oh, that's awesome. That's so cool. Brilliant. And it's like, oh wow, almost overwhelmed. I mean, it's a big subject, right? Nonlinear PDE is a big subject. Awesome. Awesome. That's super cool. Super cool. My goodness. I didn't know this one. I only know like Evans, because I never read too many books. So this is awesome. I don't actually know a lot of books on PDE. And once again, my knowledge about PDE is very much limited to the linear PDEs. So yeah, I would love to learn more. Awesome. Constant, yeah, quote unquote constant with respect to x. Excellent. Excellent. Thank you, Hot. Thank you so much. All right, so here, yeah, you can check this is correct by differentiation. All right, next example. Now, why do I write 5.3? Because that's the example number in my own notes. Let's just say example 1. Example 2. We'll have our own labeling system in case this way we don't have don't confuse. Okay, don't confuse us out. Example 2. Let's solve another PD, namely the second one. You have d squared u over dx dy equals 8x plus get free ebook online. I know, but I don't want to show this on the channel. That's the main thing. I don't want to get DMCA'd by the publisher. Yeah. So I tend to recommend free books, first of all, legal free books. This way everyone can have access to it. But as we all know, it's open secret. It's not so difficult to get free books online. But I don't want to promote it. Oh, Cupcakes, thank you very much for joining the stream again. I remember you from the mathematical statistics stream. Thanks for joining. So anyway, here, let's integrate this. Well, you can do this in whichever way you like. You can integrate with respect to, say, x while keeping y fixed. So solution, let's, here, you just start with a bigger space. It's unlikely we'll need any previous result. To integrate with respect to x while keeping y fixed. So this way you just get du over dy. So 8x after integration becomes 4x squared. And sine y is treated as a constant at this step, at least. So it's x times the sine of y. Well, as mentioned, integration with respect to x generates a constant with respect to x. So why don't we just call that fy? This is a constant with respect to x. And now you can integrate with respect to y. Okay, integrate with respect to y, you get, on the left-hand side is just u. So this should be the final step of integration. Now, integration with respect to y, meaning doing so while keeping x fixed. So 4x squared is now treated as a constant, and then times y. Okay, and then minus x times the cosine of y. Okay, x is a constant, sine of y has an antiderivative of minus cosine. And well, after integration of big F, you can write it as the integral or the antiderivative of big F dy, while at the same time, you know, we said earlier, if you integrate with respect to y, it generates a constant with respect to y. So that means you need to put a plus g of x at the end. This is the plus c, okay, in PDE. And, well, you can simply write the antiderivative of f of y as another function in y. Let's just call it h of y. So that's the general solution. So to finally conclude, u of x and y equals 4x squared of y, 4x squared times y minus x times cosine of y plus h of y plus g of x. And we should emphasize that g and h are arbitrary functions. So these are arbitrary functions, but I think it'll be a good idea to check differentiability. So h of y, so first of all, what's the differentiability of g? Well, actually, nothing is needed. Nothing is needed for g. G of x really is arbitrary. It really is arbitrary because the first step, if we to interpret the left-hand side literally, you should first differentiate with respect to y, so that means g of x is immediately cancelled out. So even when, say, g of x is non-differentiable in x in some way, it wouldn't matter. Right? It wouldn't matter. And then h of y, if you want to differentiate with respect to y, h of y needs to be differentiable. This way, at least the very first operation in the partial differentiation makes sense, right? My point is, g of x can be arbitrary, but h of y should be differentiable in y, so that the very first operation, d over dy, is is valid. So h of y needs to be differentiable. Is arbitrary but differentiable. And after that, after the first step of differentiation, d over dy, g of x is gone, and h of y now becomes h prime of y. Right? The behavior of h prime of y is irrelevant because the next step in the left-hand side is to partial differentiate with respect to x. H prime of y goes away. So there's this condition here. Okay. You know what? Let's emphasize what should f of y satisfy. F of y in the previous example can be arbitrary because differentiation is only with respect to x. Even if f of y is non-differentiable, it does not matter. Okay. F of y is arbitrary here. Okay. Awesome. Thank you very much, Hot, for writing the solution in chat. Typing things, typing mathematical expression in chat is not a fun experience, and on YouTube in general. So that's why my quizzes are mostly verbal. Perhaps you guys have seen the pattern here. Usually verbal, true and false, that kind of thing. I don't ask people to solve an equation or something. Because typically, well, when you're scrolling, it's unlikely for you to pull out a piece of paper and actually write the solution. Right? I just wanted to have some quick conceptual understanding. So that's why I don't do awful lot of equations and stuff, calculating integrals in my quizzes. But it's been fun. It's been, even with that restriction, it's been a fun activity so far. It's like it's almost like a daily ritual now. Every morning I wake up and post a question. Anyway, guys, I need to use the bathroom real quick. Be back in like 2 minutes. All right, I'm back. Oh, you know what, guys? Guys, um, I really want to eat something right after finishing the stream. So, for that reason, I'm gonna order pizza. Okay, I'm gonna order pizza. Domino's. I know, right? How unhealthy is that? Ordering a pizza in the middle of the night. Okay, I'll just do that real quick. I'll come back to the math. Perhaps show you what I ordered. Okay. So it's got to be some sort of quick order menu that I saved. All right, I'll do that real quick. Okay, almost there. Actually, you know what? Yeah, yeah, almost. I'm almost done. I was trying to be creative, but I didn't do that because I don't know what to order, so I just ordered the um, classic pepperoni. So anyway, guys, let's continue. So let's continue with the math. Okay, I was trying to show you guys how creative I am when it comes to ordering pizza. Turn out I just give up. Okay, I'm just too hungry right now to think of anything exotic. Okay, just give me something to eat, man. All right. So here, this is a second example. So first of all, so far we just use direct integration, and it would be nice if we can convert a PDE into a form that can be directly integrated, right? So that's the objective, right? So it's a very straightforward idea, even though it, of course, not always possible. Yeah, pineapple pizza next time. Is there any Italian uh, in the live stream? People would hate that, right? The Italian would hate that. So, as I was saying, like the natural goal is to write that as an equation that can be directly integrated. So why don't we take a look at this example? Example 3. So because we're in this very early stage of introduction of PDE, right, a lot of calculation requires special tricks, and that's okay. That's okay. Even though the general theory, general algorithm almost would be more satisfying, I think it's important to appreciate, especially in the very early stage, the importance of trick is almost paramount because you have so little intuition about the subject, right? So let's take a look at this more complicated example. So this is second order PDE, it's linear, and now we're given two initial conditions, two pieces of initial data. If you interpret, say, x as the spatial coordinate and interpret y as time, then you can say, this is the initial profile of the function. X, you have u as u of x and 0 is x squared. And uy, the partial derivative with respect to y, when y is 0, is 0. So you can think of this is a waveform, right? So you can think of u of x and t as the initial waveform, and uy of x and t as the initial velocity. So there's no initial velocity, but it has an initial waveform, and and we have a PDE. Okay, so how do we approach this problem? So we would still like to perform direct integration. So you can consider rewriting the PDE as follows. So there would be d over dy of du over dx minus u equals 0. 2u, sorry, 2u, not 0, but y. Here we're actually using an assumption that the mixed partial derivatives are the same. So we're assuming u is in the class C2. Assuming u is in the class C2, this way the mixed partial derivatives are always the same. Okay, this is a sufficient but not necessary condition, but the necessary condition, there's like intricacies, okay, on when mixed partial derivatives equality can fail, but we're not going to get into that. Okay. So, all right, but now we integrate with respect to y. This way you have du over dx minus 2u equals half y squared. And when you do that, you generate a constant that is independent of y. So we put a plus big F of x at the end. So this is the integration. And now let's see what we have here. Well, this is just an ODE. And this is just an ODE, and it's very similar to the one we just solved for the variance ODE. Right? In the variance ODE, we use the technique called the variational parameters. And of course, that's valid. You can do so here. A quicker method, however, a quicker but equivalent method, however, would be using the integrating factor method. Okay. Typically, in a first order PDE, in a first order ODE, linear ODE, you can do either integrating factor or variational parameters. There's really no difference. So let me just gonna put down the notes here. So if you have, this is the method, okay? This is the method in ODE. Given dy over dx, given y of x satisfies, right? Dy over dx plus p of x times y equals q of x. What you can do is that you calculate the integrating factor. Okay, this is a quick review of ODE. Yeah, this is the integrating factor. You're totally correct. Yeah, I just don't want to assume a whole lot of ODE knowledge when it comes to this stream, because some people might not seen much ODE, but anyway, so this is the integrating factor, and it's usually denoted as, you can write it as I of x, or which I like to write mu of x. So the advantage of doing so is that once you multiply both sides by mu of x, the left-hand side becomes a product rule, because mu prime of x is just mu x times px. This is mu prime of x, so which is fantastic. This way you get a product rule on the left-hand side. So the left-hand side is now d over dx of mu of x times y. And now you can integrate, in principle, of course. Right. You might still get a non-elementary function on the right-hand side. You might get, the result of the integration might still be a non-elementary function, but at least you have an explicit formula. So we're going to do that here. Okay. The integrating factor, as Chad already mentioned, is indeed e to the minus 2x. So multiply by integrating factor e to the minus 2x, you got e to the minus 2x du dx minus e to the minus 2x u, right, which equals half e to the minus 2x y squared plus f of x times e to the minus 2x. And then we integrate, so we get d over du, partial derivative, d over dx, e to the minus 2x times u, times u, and then equals half, half of e to the minus 2x y squared plus f of x times e to the minus 2x. Oh, I forgot to mention that big F is arbitrary, right? And we assume that u is C2, Assume that U is C2, so what should F be like? Big F is arbitrary. I'm not sure. So if, let's say, F is differentiable, certainly there wouldn't be any problem. But let's just call F arbitrary. Now, we'll see how things turns out at the end, okay? So this is what we got so far, and now we can integrate on both sides. So now you can integrate over x with respect to x partially, treating y as a constant. Once again, e to the minus 2u times u equals, this is negative 1 over 4 e to the 2xy squared. Okay, and then plus the integral of f of x e to the minus 2x dx. There's nothing you can do here. All right, let's not forget there is a function. Oh, sorry, here this is not minus 2u, but rather 2x. Okay, so there should be another function, arbitrary function at the end. But the arbitrary function should be independent of x, so it should be a function in g, let's say g of y. And that is pretty much it. Okay, so that is pretty much it. So you can rewrite now u as a function of u of x and y as minus 1/4 y squared. I think you wrote wrongly. Okay, something is not incorrect. But chat, which line? Hot. Here, let's just say this is line 1. Okay, line 1, 2, 3, 4, 5. Which line is incorrect? Okay, starting from the first line. Okay, starting from this part. This is okay. Integration, integrating factor, yeah. Write the left hand side as a product rule. The right hand side, nothing happens. Integrate. Integrate, you get minus 1/4 e to the minus 2x y squared. Should be, oh, did I? Oh, here. Yeah, for some reason I didn't make a mistake here, but yeah, up there you're definitely right. Yeah, this is minus 2x. Yeah, somehow I kept things correctly down here. Yeah, thank you very much. Thanks. Yeah, awesome. Thanks for paying great attention to detail. This is great. But notice that this big term here can be written as h of x. This is just another function in x. Okay. So here, this is our general solution. Awesome. Yeah, this is our general solution. Yay, problem fixed. Let's just call this our general solution is u of x and y equals minus 1/4 y squared and h of x plus e to the 2x g of y. Right. The reason I didn't spend much time discussing, what sort of differentiability we need here is because we have the initial conditions at the end. We don't really care about general solution per se. We just wanted to get to the solution to the initial value problem. Okay. All right. So we need uy. Right. So uy is minus 1/2 y. H of x disappear, and then e to the 2x times g prime of y. I'll be back. Okay. So uy is this thing. ui, the partial derivative with respect to y is this thing. So now let's substitute. Use the initial condition. So ux of 0. Okay, let y equal 0, so the first term minus 4y squared goes away. Get h of x times plus h of x plus g of no, not g of y, but rather, hold on a second. This is what? This is e to the x, e to the 2x times e to the 2x times g of 0. G of 0. This is supposed to be x squared. Yeah, this is supposed to be x squared. We need to solve for the unknown function. That's our goal. And uy of x and 0, use the initial condition again. Actually, first of all, substitute. Setting y equals 0, minus half y disappears. And e to the 2x times g prime of 0. E to the 2x times g prime of 0 should be here, should be 0. Should be 0. So, what do we have here? So, well, the second equation looks easier. And by the way, this should be 0 for all x. The initial condition is given as a function of x. Here, so you can see initial condition, doesn't matter is u or uy, should be a function of x. So that's why the second equation, the second initial condition tells us that g prime of 0 should be 0. G prime of 0 should be 0, right? I think so. G prime of 0 must be 0. So therefore, g prime of 0 must be 0. Do we have enough information? I hope we do. It feels right? Because you have a second order PDE and you have two pieces of initial data. Even though we're not trying to prove the existence or uniqueness or anything like that, it should be valid. G prime of 0 should be 0. All right. So what can we do now? What can we do now? We need to solve for h and g. That's our objective here. So can we write, well, let me just put it this way, okay? So the second initial condition says g prime of 0 is 0. So what is h of x? Well, h of x is x squared minus e to the 2x times g of 0. There's that. All right. This is a function in uy as a function of x and y is this thing. So can we specialize this and say, here, can we specialize and say, say uy, when you set x equals 0, this is what I mean. Because from these initial conditions, you only have information about g at a certain point, at y equals 0. But we need g of y in general, so let's consider considering setting x equals 0 in uy. So this way you get minus half y and then plus g prime of y. G prime of y. So what should that be? Think about what should that be, because the second boundary condition says here g the second boundary condition says this should be 0, right? Hang on. Actually, I think I miswrote. I think I miswrote. My bad. I think I miswrote, guys. This is not what is given. Okay, this is not actually, guys. This is actually not what is given. So this is actually given as uy of 0, y. My bad. My bad. Okay. This is the original note. Okay. My bad. Okay. Changed it to this thing. All right. So here, I mean, this needs to be changed. Okay. My bad. Uy of 0y. Okay, uy of 0y is what I have here, which equals 0. Okay. I think for the general wave equation, that has to be handled differently. If you're, let's say, given the original format, the original shape, and the this is more like a boundary condition. This is a boundary condition. If you treat x as a position and y as time, then this gives you the original profile, and this tells you what happens at the endpoint for all time. Okay, this is a boundary condition, and this equals 0. This way, g prime of y, sorry about the confusion earlier, because, totally my fault. G prime of y is now half y, and as a result, g of y is 1/4 y squared plus c. Okay? Plus c. And what is c then? What is g of 0? Remember, earlier we have a g of 0 here. And as a result, g of 0 is just c. G of 0 is just c. Okay? So now let's consolidate everything. U of x and y is minus 1/4 y squared plus h of x. H of x is x squared. Right, so far I'm just doing direct integrations. Right, so that's what we're doing. And the method of characteristic is actually can be viewed as a generalization of direct integration. Okay. As a first understanding. Okay. G of y is plus e of x times g0. G0, as I said, is c. Okay, and then plus e to the 2x times g of y, where g of y is quarter y squared plus c. So this way, e to the 2x times c cancels, and you get the final answer, which is x squared plus 1/4 y squared e to the 2x minus 1. And we're done. And of course, it's worth double checking the answer. So check. Okay, first of all, the initial condition and boundary condition, u of x and 0. Okay, when y equals 0, then it's just x squared. So check. Boundary condition, uy when x equals 0. So we would first differentiate with respect to y here. You get half y, and then times e to the 2x minus 1, and then set x equals 0. So this is indeed 0. That's also correct. Boundary conditions matched. And also, of course, the PDE itself. So let's first calculate. We need du dy. Okay. Du dy is half y e to the 2x minus 1, and then also d squared y over dx dy would be y times e to the 2x. So is this the same as, say, here, 2 du dy plus y? 2 du dy would be 2 times 1 half y times e to the 2x minus 1 and then plus y. Yes, this is correct. This is correct. So now everything checks out. Okay, so that's our third example. Once again, using direct integration. Okay, using direct integration. So now let's take a look at a different situation. So we're interested in the scenario where you cannot do direct integration. Right? These are the norm, actually. So definition, the DE, first order PDE, first order linear PDE would have the general form for, once again, u of x and y has general form as follows. Okay, so guys, don't worry. I mean, we'll at least give one example of method of characteristic in this stream because it's in the title. So of course, I can always modify the title later on, but I still wanted to cover at least one method, one non-trivial method. Okay, one method that is fundamentally a PDE in its nature and not just already covered in ODE, right? Earlier, like here, this is just integrating an ODE, integrating factor. Right here, we want to introduce the genuine PDE method. Okay, so that's a first order linear PDE, has a general form. So actually, hang on. I need to pick up a call. Yeah, I'm just grab my wallet real quick. Thank you. Guys, pizza delivery is here. Don't worry, I'll be back. I'll be back in a few minutes. Okay, sorry guys. Yeah, just get the pizza at the door. Anyway, so I just realized that the definition, the so-called definition I gave on Saturday was not quite right. So actually today is the 3rd. My bad. So the note should be, hang on, oh, I was keep writing the same note after this one. I guess that's fine, but it's just that the note is getting too long and it's getting ever more laggy. No wonder tonight is a little bit laggy. So anyway, coming back to the definition earlier, which I gave on Saturday, but that's actually not the general definition. I said this is general, but this is actually incorrect. Okay, because I missed that there should be a U term. So in general, it should be not just the derivative in U, but also the term for U itself. Okay, so that's a big mistake. I'm terribly sorry. So here it should be as such. You got the linear terms in du dx, du dy, and also U itself. And on the right-hand side, you can have a so-called inhomogeneous term that only depends on the independent variables, x and y. Okay, so here it should be f of x and y at the end. Okay, so that was a big mistake, actually. And the same thing for the quasi-linear. For the quasi-linear, you would just add an extra u in all the coefficients, including the one on the right-hand side. Okay, so yeah, this needs to be fixed. It's a big mistake, actually, because the u term can also appear in the PDE. Okay, so there you go. And now coming back to this definition, our goal is to do a change of variable so that the d is directly integrable. You can use integration technique from the first order. So not the first order, from the first order ODE. So that's the idea. Okay. So let's take a look at a special case. If, let's say, b is 0, then you can treat y as a constant, because only partial derivative involved is ux. Right? So the idea is, let's say if one of the partial derivative is missing, one of ux and uy is absent. If one of ux and ui is absent, then just say ui absent. And then what happens? So you got a of x and y times ux plus, well, b is 0, right? So i.e. b is 0. B is a constant equals 0, and then plus c of x and y u equals fx and y. This way, y can be treated as a constant, as if this is an ODE for u as a function of x alone. Y is simply just a parameter. Then the PDE is essentially an ODE. This is an ODE for the function u of x. And y is treated as a parameter, i.e. y is treated as a fixed. And there wouldn't be any issue, right? So our idea is to introduce a change of variable that can eliminate one of the derivatives. So that's the idea here. So how can we do that? So how can we do that? So let's consider the following. So we want a change of variable. So we want a change of variable so that one of the derivatives is removed, right? So for that end, let's consider a change of variable. And because we don't have an awful lot of time left, let's just do a simple example. And we'll do a simple example here, and we will give the most general method characteristic later. So here, just do a simple example. And actually it is also inspired. Where the hell is my nose? Yeah, and it's also inspired by our very first example of the traffic flow. Although we're going to do a simplified version of the traffic flow. So in the traffic flow, we have these quantities: the density, the flux, as well as velocity of traffic. So there, we assume that V depends on rho. In general, V depends on rho, and that's actually what makes the traffic flow problem interesting, because as the density grows, cars drive slower. But let's imagine you have just a simple situation where V is constant. So imagine V is independent of everything. V is just a constant. So in that case, the conservation law here would just be d rho over dt plus d rho over dx, and then times V equals 0. Right? And that's the simplified traffic flow PDE. It's the same continuity argument, same conservation law argument, just we're going to specialize for a special case. So here, this is an example, and this example is known as the linear transport phenomenon. Linear transport phenomenon, and it's described as follows. So in the traffic flow PDE, linear case. So let's say this is the traffic flow PDE, d rho over dt plus d of rho v over dx equals 0. Remember, rho v is flux. So if, let's say, v is constant, then you have rho t plus v rho x equals 0. Okay? And you have that. What now? What can we do next? Well, let's consider a change of variable. So that one of the derivatives can be eliminated. Consider a change of variable, say, hang on, let me say you have d, say, xi equals t, and eta equals t plus vx. Say, if you have that, then what would be the new derivative? Say, this is rho, by the way, rho depends on x, and t, x is a function of xi and eta, t is a function of xi and eta. Okay, so what is rho t? Rho t would be d rho d xi So let me redraw the diagram here, okay? So I wanted to have rho and xi. So rho depend on xi and eta xi depend on t and x in general. Okay. So d rho d xi times xi d xi dt. And that's actually all we needed because it's independent of x here. So that's just d rho d xi. And what would be, say, rho x, because that's the second derivative, not second order derivative, but the other term that appears in the PDE, right? So rho x would be, rho x actually, that's actually, the change of variable might need to be changed, but let's just do it regardless. D rho over d d xi, right? And then times d xi over dx, and that's 0, and then plus d rho over d eta times d eta over dx, right? Just a chain rule. Just a chain rule. So here you have something isn't quite right here. D xi over dx is 0, and the second term is d rho over d eta times d eta over dx, which is v. Does that give us the cancellation that I wanted? I want to have just one derivative in there, because I want to cancel out one term. Actually, you know what, guys, because I don't even know, might be a good idea simply to derive the change of variable. I don't know, because right now I can't say. I just have this vague memory that the change of variable should look like something like I just wrote, but I'm not sure actually. Let's just derive it from scratch, because this will actually give us the general principle, I believe. Xi in general depend on t and x, okay, and eta in general depend on eta t and x. Eta should be a function of t and x. So, because I forgot what would be the right change of variable, so why don't we just derive it from scratch? I mean, if I remember things correctly, this actually might look like a magical thing, but really, if I derive it from scratch, perhaps that's more clear, and we'll do so in the general case next time. So now you just write the classic chain rule, okay? D rho d eta and d what's that? D eta d t, right? And then let's do the substitution. So the goal is I wanted to cancel out one of the derivatives. I want, let's say, only d rho over d xi. So substitute rho t. This way you get d rho d xi times d xi d eta d xi dt plus d rho d eta dt. That's rho t, and then plus v times rho x. Rho x would be rho d rho d xi d rho d xi, yeah, times d xi over dx, and then plus d rho d eta over dx equals 0. So rearrange according to the partial derivative of rho. So this way you get d rho over d xi times d xi over dt plus v times d xi over dx. Right, that's d rho d xi, and then plus d rho d eta times d eta over dt plus v d eta over dx. Okay, I want this to say, I want this to be 0. I want this to be 0, so this way I can do direct integration. So want it to be 0. So let eta to be, how can we vanish this? A simple choice would be, say, let d eta over dt to be minus v, and d eta over dx to be 1. Can we make that happen? Yeah, of course we can. This is just a linear function. Eta would be x minus vt. Okay, x minus vt. And on the left, we still have to choose another function. We still have to choose the zeta here, but it shouldn't really matter what we choose as long as zeta and not zeta but xi and eta together forms an invertible transformation. Because our primary objective is to eliminate one of the derivative, and now by letting eta to be x minus vt, we already managed to do so. So why don't we make our lives as easy as possible to say, okay, I just want this to be 1. And to do so, you can simply, once again, the choice is not unique here, but you can simply pick xi to be t. Right? So thank you, Gwendolyn, for joining the stream. Yes, my discussion on the vacuous shoes case was a separate video I made almost a year and a half ago when I first started the channel, because I felt like this topic was not very well explained in most books I've seen. So yeah, as I was saying, like here, of course, these are non-unique choices, right? Our objective is to simply eliminate one of the partial derivatives so you can directly integrate. And so that's the transformation we're going to choose. And of course, this is obviously invertible. You can solve for x and t from zeta and t, from zeta and eta. And that's actually our first understanding of the Mestel characteristic, is to eliminate partial derivatives in the original PDE so that it can be directly integrated. Okay, we'll investigate the meaning of these transformations later, but that's perhaps for me, this is is the easiest way to understand Mestel characteristics. Now, of course, this is a very limited situation. Mestel characteristic later on can be applied to a quasi-linear situation as well. But for a linear case, this is enough. You just want to eliminate the derivative so you can do direct integration. And this way you get just d rho over d xi equals 0. And what do we know about the solution of this one? Well, you just integrate over zeta, or sorry, over xi, and this way you get rho as an arbitrary function, of eta. Right? And which means it's an arbitrary function of x minus vt. Okay, and suppose now we have the initial condition. So suppose now, let's say, not only we have the PDE for the linear transport phenomenon, we also have the initial condition. Say you have rho of x and t, rho of x and 0 equals some initial profile. Here f is arbitrary. Here f is arbitrary. Let's say if you have some initial profile, say phi of x, we can solve for phi, solve for f. Yeah, I can't keep up with this many streams. I know, right? Sorry. Last week was, I promise, last week was very much an anomaly. Because I just wanted to make as much progress as possible, even if I say just do the math myself without recording it. I figure I might as well just record the whole thing. Could be helpful for someone. I hope most people would not interpret this as me spamming, because this is literally me doing actual math, right? But it doesn't matter. I think I'll say this, okay? The streaming content will be condensed into more structured videos. Okay. So this way, like the tensor stuff we did last week, as well as measure theory and all of those things. Okay, the streams will be, which you can consider as the behind the scene, because right now I think I'm suffering from writer's block right now, and I want to overcome that by just practicing more math. So yeah, let's solve for f. Setting t equals 0 above just gives you f of x equals phi of x. So f is now solved. Therefore, rho is simply phi of x minus vt. But what is that? This is just a translated version of phi. This is right shift. This is the right shifted. Remember here, I mean, of course, if you assume v is positive, okay? This is a right shifted version of phi. So this is actually very insightful. It says physically, if the traffic speed is independent of everything else, if it's just a constant, regardless of the density, then the density rho as a scalar field would simply be transported along the direction of the velocity and at the same speed as the velocity. Okay, so that's what is about. So let's say this is the original profile. Can be an arbitrary function. This is phi of x. Okay, this is what the initial profile is like, t equals 0. And now after say some positive time, what happens is that you're just going to transport this to the left, to the right, if v is positive. Okay, so that's pretty much the interpretation of this model. And of course, this is a very simplistic scenario, but it's useful nonetheless. Right? This model comes from fluid dynamics. Actually, do not underestimate this model. This is actually a good testing case for numerical methods. What do we mean by that? Let's say you develop a method for solving PDEs numerically. The very first thing you should try out is the linear transport equation. Not just because it has a simple analytic formula that you can check against, but because the solution here has exhibit a property called the stability. Because this is just a translation, at any time, if the initial condition is bounded, typically it is, if the initial condition is bounded, then for any time, the solution should remain bounded. And this is something that we call stability, numerical stability in numerical analysis. That is to say, we hope that the solution is stable. Let's say if you have a numerical method, in the process of executing the algorithm, when you do the calculation on a computer, inevitably you would make small mistakes, like rounding errors. Numerical stability tells you whether those little errors would compound. Right? So if a numerical method is stable, right, then the solution would remain bounded. And in particular, the small little errors remains bounded. If the errors would compound and blow up, then eventually you get just pure garbage. Right? So even though this little solution is very simple, it is an important test case for numerical PDE. Whenever you have a numerical solution, say like the finite difference method, some sort of finite difference method, you should first test against this simple scenario and see if there's any situation where you get instability. Okay, so that's a non-trivial application of this solution. But the main point here is that we can understand the so-called method of characteristic right here. This part right here is the method of characteristic as a first understanding. Later on, we will see a more general version of it. Right now, it's just a change of variable so that you can eliminate terms in the PDE. Okay, and that will be it for today. I'll see you guys next time. Okay, bye.